All right, Munchkins, this is the Wizard. Welcome you back to Introduction to Computer Vision. As you can tell, I'm sort of energized, and I've taken some time off, about a year or two. So anyway, what we're going to do this time is start working on tracking. So the last unit, or at least some previous one, hopefully, that depending upon the order in which you're viewing these, we were looking at motion, which was sort of the change in imagery between two successive frames. And that change could be due to a change in viewpoint, multiple cameras, or a change in time. You're watching something move for a while. This unit is going to focus on tracking, where objects are moving over time, and the computations that we're doing are to keep track of them. And it is sort of a fundamental part of computer vision these days, although a lot of what we're going to be talking about will eventually get into things that come from the domain of robotics, because there's been a lot of work done on sort of how you keep track of things over time. We'll do a lot of modeling. Also want to say, again, a bunch of slides adapted from Kristen Grauman, Deva Ramanan, and Svetlana Lizebnik. And Svetlana, if I messed up your name, I'm sorry. Let me just show you some examples of what we mean by tracking. Here's some slightly older ones. The one on the left here, this girl jumping around. You see a little red ring around her head. I think that's Andrew Blake's daughter a long time ago. I think she's now a lawyer, so that tells you something about the time difference. Andrew, I have no idea if that's true. And also from the similar work is this leaf blowing in the wind. And you'll notice as the camera zooms in and out and things move around, it does a pretty good job of sticking to the leaf. Both of these examples were work that Andrew and Michael Izar did in the particular type of tracking that we'll actually do, not this lecture, but a couple lessons from now. Here's a slightly more recent one. This is a tracking of body parts as somebody's moving. You can see the reference there. And again, this is a tracking problem, but it's tracking with a model, right? So the idea is I want to be able to track where the parts have moved. Here you see a sort of a more traditional notion of tracking, but in this case it's lots of targets, right? So there are a lot of people, say, walking around in the street here, and you'll notice that it does a really good job of keeping track of all the people, the little box that's around each one of them, and there's another little box that's on their head. Here there's just a little bit of an animation showing you that it's tracking them through space-time, right? So this volume with these trajectories through there is showing you how it's doing the reasoning over space-time. There are a couple of interesting things to notice here. Watch this guy going behind the pole, all right? So he goes behind the pole, and he appears the other side, and you might ask, how does it do that?
How does it do that?
I'm not going to tell you yet. I'll tell you soon. And also here it's showing you just the heads that have been tracked to show you that it's recovered that. So this is an example of sort of a state-of-the-art tracking, at least of a couple of years ago. As we mentioned, so far we've only done flow estimations in pairs of images. Now, one way of thinking about doing tracking is if you had more than two images, you could do some form of optical flow or some sort of motion between one image and the next, and then you could just do it between the second image and the third image and the fourth. Basically, you would just sort of follow the arrows, connect the dots. So there are a couple of challenges to just doing that. One, as we saw, it's hard to compute optical flow everywhere. You have to have just kind of the right types of behavior for the gradient in terms of being able to track these features. Second, there might be large displacements. So between one frame and the next, something may have moved a lot. And so there's a lot of search that has to be done. And so one way of doing that is you might want to take the dynamics into account. How is this thing moving? Make a prediction. And in fact, that's what we're going to spend a lot of time talking about over the next couple of lessons. The other problem with sort of connecting the dots is things will drift. That is, I make a little mistake and then a little more mistake, and eventually I'm no longer tracking the thing that I had started wanting to keep track of. And then finally, another problem is what are called occlusions or disocclusions, right? Occlusion is when something gets occluded. Disocclusion, maybe unocclusion is a better word. Basically, it appears from something. So something appears. Was it something that I had lost before, or is it something new? And how do I do that kind of tracking? We'll start with one very simple description that you've actually already seen, right? We talked about the Shi and Tomasi feature tracker, and basically it's this idea of only compute motion where you should. We talked about this when we talked about the Harris corners, and we talked about how to analyze that second moment matrix. And we said, well, there are other ways of analyzing that second moment matrix, including the eigenvectors and eigenvalues there. And we said that there was this Shih-and-Tomasi thing called good features to track, the thing that OpenCV made use of. And basically, the idea was that just track points that you can track reliably. Their basic algorithm was the following. You basically, from frame to frame, you're going to do Lucas and Canati pure little translational motion, right? That, remember, the idea was that we assume that within a given small patch, we're going to find some translation, all right? And what's nice about that is that's pretty robust for sort of small neighborhoods. You know, you can basically say that they're all translating. Then what you do, and we're not going to go into this too much here, is we're going to take those points that have moved and look for an affine consistency. So the idea is for each of the little points that you've tracked using the translation, is there an affine model that maps the tracked points to the original points? And then you can compare those back to the original. And that's exhibited here. So here's an initial image, and you can see this little sign in there. It says 25 miles an hour, and here they're getting closer, and here you're zooming past. So the sign is both translating, right? It's moving to the left in the image, and it's also expanding, all right? And here you can see the frames that have been recovered, or I should say you can see the region that has been recovered through the tracking. And the idea is that all the points in the sign, remember it's on a plane at moderate distance, which means it's a perfect affine transform. All those points are moving in a particular affine transform as you move across the image sequence. And like I said, that was this good features to track, which later got incorporated into OpenCV for doing estimation of motion. So we mentioned that you could use Lucas and Canati between frames and use the Shih-and-Tomasi way of finding features, small displacements. But what if there are large displacements? What if things have moved a lot because they're moving quickly? Well, one thing we do is we do know that we can build a descriptor, remember the SIFT descriptor, so that if you found a matching point, I would be able to say, yeah, I'm pretty sure that's a match. But the question was, how would I decide where to find it? So when we were doing the ransack method of finding those panoramas, you remember we essentially compared all of these with all of those, found the putative matches, selected a bunch, and then tried to find something that gave us a consistent model. So you're doing a lot of work in order to try to globally find all of these kinds of things. For tracking, what we want is, well, first of all, we typically want real-time methods because we want this thing to operate as things are moving along. And in particular, we want this notion of a coherent tracked result, right? So we're not going to try to match everything in one frame to everything in another and then do it again and then do it again and do it again and do it. See, so you just saw my head rotating around. I hope you're paying attention. So the idea is that you have this smooth, coherent trajectory. And that's what we want to do for tracking. And in order to do that, we have to worry about the dynamics. That is, how are things moving? How are they changing? So when we do tracking with dynamics, the key idea is we've got some sort of model of the motion, and maybe we're updating that model, like the velocity and the acceleration. But using that model, we want to predict where the objects will be in the next frame, and then we're going to look around that area, okay? And that prediction will allow us to restrict where we're doing the search. And the other thing is, if we have a noisy detection, that is, our ability to know where this thing is not perfect, we should actually get a better overall estimate because we're combining a prediction with the measurement. So that's the idea of tracking with dynamics. Fundamentally, the use of dynamics is what's different between just doing detection and actually doing tracking. And that's shown as an example here. Here we have 20 frames taken, and here's some dude right there. You can see that he's walking across all these, and we just like to keep track of him. And of course, he's changing his appearance every frame. He's not going to look identical from one frame to the next. So detection, we independently detect the person each time, right? So we maybe have a little model of what this person looks like, and we run it maybe all over the image, and we say, aha, you know, he's here. Aha, he's here, aha, he's there, and just he's there. No more ahas because it's like not exciting anymore. Okay, so that's detection. Tracking, we do a little different. What we do is we predict the new location of the object based upon the estimated dynamics. And I say estimated dynamics because, for example, this guy, he's walking, so maybe he's got a constant velocity, but we don't know what that velocity is a priori, right? We have to estimate it, right? So here we have an example where we detect him here. And it says, we'll estimate the velocity, but maybe we estimate a zero velocity, or we have some prior reason to believe he's moving to the left, because this is a sidewalk where people move to the left often. Fine. That allows us to make a prediction in the next image of where that person will be. And then we detect them. So now we can do two things. First of all, we can improve our estimate of where he is based upon both our detection and our prediction. And second, now we do have a reasonable estimate of the velocity. So we can use that velocity to predict in the third frame, detect, et cetera, and we iterate. So this is what the basic tracking loop is. As we said, the key idea is we're going to use this model of motion to make these predictions. And there are two goals, right? Goal number one is that we can do less work because of this. Because we have some idea of where the object is going to be, we can restrict our search. Goal number two is we should be able to actually improve our estimates because we're using both predictions based upon dynamics and our measurements. Now to do this, we're going to make certain assumptions. Okay? And the assumptions basically come down to the notion that this is some form of continuous motion. We're going to assume that objects don't disappear and reappear instantly somewhere else. For those of you in child psychology, that's a whole Piaget thing. Kids don't come to that belief until, I don't know, it's like a year and a half or something like that. So like kids who are really little, if you take a toy truck and you've got a screen here and you put the toy truck behind the screen, and then you lift up the screen and the truck's not there anymore, they're not surprised. Things disappear in their universe all the time. Or it becomes a carrot. They're not surprised either. Then all of a sudden they get to a certain age when the truck comes back, if you pick it up and it's a carrot, they're like, whoa. All right? And that requires a certain change in a mental model. Okay, I don't know why I mentioned that. It's just really cool. It's true, by the way. Not that Piaget is all true, but that's true about children. Anyway, so we're going to make our assumption in our tracking that things don't just appear or disappear. We're also making an assumption that the camera doesn't move instantaneously. Because that would be the same thing, right? If I instantly went from here to here, right, big change, things will have violated my apparent continuous motion. So that's basically that there's this gradual change in pose between the camera and the scene and the object. So that ends the introduction to tracking, basically saying that what we're going to do is use a model to make predictions, take some measurements, and integrate it. Like I said, it's not strictly computer vision because it involves state estimation, which comes from all sorts of parts of engineering and robotics and things like that. But it's what's required in order to make the tracking to work. So we'll sort of take a little bit of a detour to talk about state dynamics and estimation, a little bit of robot localization using visual features, and then we'll get back to fundamentals of tracking using these methods. Cool. All right, welcome back to Computer Vision. Today we're going to continue, well actually we just introduced tracking and now we're actually going to do some. So remember last time we talked about the difference between detecting and tracking. Detecting, we have some operator and we just find whatever our target is in every frame. In tracking, we're going to predict the new location of an object or the expected distribution location of an object using estimated dynamics. So somehow we're estimating the velocity, accelerations, whatever. And then we're going to update based upon the measurements that we take. So that's sort of the, shall we say, the intuitive way of describing it. What we're going to do this lesson, the next lesson, the lesson after that, I don't know, probably for the next 8 or 7, 12 years or so. What we're going to do is we're going to make this much more formal. And basically, tracking as a form of inference. And what we mean by that is we're going to have some state of the object, some state we're trying to estimate. We're going to call that x. That's the parameters we care about. But we don't actually know that. So we refer to that as being hidden. And we have a sensor. Typically it's going to be a camera for the stuff we're talking about. And what it's doing is it's taking some measurements. It's measuring like our raw detections that we were doing before. And we're going to refer to those as noisy observations of whatever the underlying state actually was. The system that we're assuming is that at every time step t, the underlying state changes from x of t minus 1 to x of t. So here we have x of t minus 1 to x of t. And then at time t, we get a new observation. We get a new measurement. And our goal, your mission, should you choose to accept it, is to recover the most likely state time t. Now, I was thinking about that. It's actually, that's not quite right. What you want to do is you really want to estimate, not the most likely state, I'm going to cross that out and say the distribution or density. So if I have the density, that is, I have some belief about where x might be, I can tell you the most likely place. That would be the highest probability. I can tell you the average guess. That would be the expected value. But the idea is that we're going to have a density. And so your goal is to recover or estimate this distribution given, first of all, everything you've seen so far, right? So you've been taking measurements all along since last Tuesday. Where is this thing now? And the other thing that was given to you was some knowledge or some model of the state dynamics. That is how this thing moves. Now, you may have to estimate some of the parameters, but you may know that, I'm going to assume that this thing has a particular velocity and the acceleration is just some noise. That would be a model that you're going to assume is known.
So what do we exactly mean by state and measurement? Let's try to understand with an example. Say you're looking at a pendulum, swinging back and forth, and assume that it has a marker on it that you can detect reliably using one of the corner finding or template-based matching techniques you've learned so far. Now we can identify different quantities to describe this system. For instance, the center of the target can be located using an x and y coordinate. Similarly, the pendulum rod has a certain length. Let's call this L. The circular weight at the end has a radius r. We could even say that the pendulum makes an angle with the vertical line. Let's call this theta. When defining a model for this system, which of these quantities would you include in its state, and which quantities are directly observable from images? That is, part of the measurement model. Again, the quantities we are looking at are the xy location of the target, the length of the pendulum L, the radius of the circular weight r, and the angle made with the vertical theta. Mark the appropriate checkboxes. If you think about it, the only thing that we can directly observe is the xy coordinate of the target. Yes, we could try to detect the pendulum rod or other components, but that may not be as reliable. So this is the only thing that needs to be in our measurement model. The same xy location can serve as our system state. However, since the motion of the pendulum is constrained by the fixed length rod, assuming it is fixed length, it's better to compress the state. It really only has one state variable, that is theta. Again, this is assuming that L and R are constants. When analyzing a dynamic system, it is very important to identify what are its real degrees of freedom. Sometimes the state variables you need to keep track of may not be immediately apparent. We will see examples of such systems later on.
So to give you, again, still a little bit intuition, but getting a little more formal. So here we have that same person walking at time t, and then there's a question of what do we do at time t plus 1. And the idea is that from time t, we have some prediction or some belief that's indicated here in red of where we think the person is. Okay, and that's our prior. So before we take any measurements at time t plus 1, this is our belief. By the way, I will go back and forth. The slides sometimes go back and forth between whether we're talking about moving between t minus 1 and t or t and t plus 1. It doesn't matter. It's just going from one step to the next, and sometimes I screw up one way, sometimes I screw up another way. This is like the story of my life. All right, so at red we have, the idea is we have some prediction at time t, and we want to know what's happening at t plus 1. At time t plus 1, we take a measurement. That's what's shown here in green. Okay, so we had some distribution that was our belief about what's there, and now we have some measurement. Now notice that this measurement is also a distribution. We're going to talk in a little bit about what that means. It means two different things. One you can think of is that given that the person is someplace, how likely would be the current measurement that I got? So you see here, let's assume the measurement was there. Okay, this distribution says not how likely is the person at a particular place. That's what I'm trying to estimate. What this distribution says is how likely would this measurement be, how likely would I be to get this measurement if the person was at these different locations. That's a little confusing. When we do the math of likelihood, that'll become clearer. For now, you can think of a measurement that's just a little bit noisy. I don't know, it gives me some bounds on where the person probably is. And then finally, taking that prior belief or prediction and the measurement, I come up with what's referred to as either a corrected prediction, final estimate, or the technical term is the posterior distribution as to where I think it is. And that's what's shown in blue. So I go from a prior or an old belief to a measurement, to a new belief. Writing these out as equations, so the prediction can be thought of as this way. What is the next predicted state of the object? Here I'm back to x of t given t minus 1, given all the previous measurements, okay? So you see here that it says given y from 0 to t minus 1, so those are all my measurements up until before t, make a prediction at time t. Correction is, again, I want a distribution. Remember, I'm coming up with a probability distribution of xt. Given what's new, well, what's new is I have my new measurement, okay? So basically, this was my prediction based upon my measurements up until t. Then when I'm done, I should have a prediction including the current measurement. So basically, the tracking is this propagating what's called, as I said, the posterior distribution, posterior density of state given the measurements. So this term here, this is my posterior because it's after I've taken the measurement at time t.
Wait a second. Why do we need probabilities? I guess it makes sense for prediction, because we don't know what the value of x is at time t, since we only have information till time t minus 1. But what about correction? We know what the measurement is at time t. Why can we not get a definitive value for xt? Why is this a probability distribution? Is it because the state and measurement are different quantities? Like in our pendulum example, where we said the state could be just the angle theta, and the observation was the location of the target. Or could it be that observation values are unreliable due to underlying sensor noise or even imperfect detection algorithms? What if observations are missing or beyond known limits? Is that a good reason to model state as a probability distribution? Let's think about the first point. Our pendulum example is one where x and y are different quantities. However, this is not a strong argument. Here our state can be precisely computed using the observation. It is merely a more efficient representation. However, there are other cases where the difference between state and measurement is more important. You're looking at a clown juggling 3 identical balls that you want to track. You have an excellent detector that, given any video frame, spits out 3 xy coordinates that are the centers of the 3 balls. This is your raw observation, x1, y1, x2, y2, and x3, y3. There is no guarantee that x1, y1 refers to the same ball across frames. Clearly, you need something more in your state model. How about velocity, including direction and magnitude? That would help you predict better which xy belong to which ball in each frame. There are many other situations like this where directly observable quantities do not suffice as the system state. Therefore, the first point is valid. More importantly, you need to realize that detection techniques, especially dealing with real-world data, are not always 100% accurate. Noise can be introduced into observations due to various reasons. Sometimes just the discrete nature of digital images results in observations that are not smooth. It is best to take observations with a grain of salt. Remember the video where that guy walked behind the pillar? That's a missing observation. If you didn't have anything more in your state, where would you say the person was? Well, you could say that it is highly likely that the person is nearby where they were last seen. Therefore, the last point is also a valid reason for modeling these as probability distributions.
To do this, we're going to make some simplifying assumptions. The first assumption is a Markovian assumption, and that's that only the immediate past matters. So what this says is, if I know all of the states up through t minus 1, and I want a prediction of the state at time t, that just depends on the state at t minus 1. Now, these are x's, not the y's. These are if I actually knew the state. What this tells me is, if I wanted to predict the state on Wednesday, and I knew the state on Tuesday, Monday, Sunday, Saturday, it's all the same as knowing the state on Tuesday, okay? I only have to know one prior state. Now, some of you might ask, but wait a minute, if I know Monday and Tuesday, I might be able to estimate the velocity for Wednesday.
If I know Monday and Tuesday, I might be able to estimate the velocity on Wednesday.
So that's right, except not, because your state can also include the velocity, right? So if I knew the position and the velocity on Tuesday, I make a prediction about Wednesday. So this is the Markovian assumption. This probability of xt given xt minus 1, that's what we refer to as the dynamics model. That's how things are changing. Second simplifying assumption, we're going to assume that the measurements, the probability of the measurements, remember these are noisy measurements, given everything in the past and the current state, only depends on the current state. So this is where we say that the probability of a measurement given a particular state and everything else only depends upon the state. By the way, this is called the observation model, and I will tell you it is this particular assumption that is sometimes the most suspect. One way you can think about this, suppose you have some noise in your sensor that is related to some other processes going on, and it changes in a particular way that you might be able to estimate. This thing says, well, I don't look at my previous measurements in order to make that prediction. So for everything we're going to do, we're going to make use of this observation model where the likelihood of the measurement depends only on the current state. Just know that for more advanced things like conditional random fields and other approaches, we're actually able to make the current measurement tied to previous measurements. But we're not going to do that here. I know some of you have taken various machine learning courses and you're familiar with graphical models. And if I were to draw up this set of simplifying assumptions as a graphical model, it would look like this. And what this says is that some state x depends only on the state at time t, depends only on the state at time t minus 1. And furthermore, it says that my measurement depends only on the state. And whenever I look at that, I always think to myself, okay, that's a joke. Why? Because those of you who know what this is a hidden Markov model, an HMM. See, now Megan, who was helping me with the slides, she didn't know that, so she didn't know how funny that was. So she's now, what is it, ROTL? No, ROTFL, sorry, I left out the floor. It's really hard to say emoticon things. Not emoticon, what do you call those things? Whatever they are. Now she's getting up. Another way of thinking of this is that tracking is just an induction process, right? Induction, like from math, is if I know how to do n, then I know how to do n plus 1. When you show what the sum of a geometric series is or things like that, you tend to prove these things by induction or something like that. So for induction, you have to have a starting case, a base case, so you have some guess as to how things start. Maybe for our tracking, we have some distribution. It could be a very uncertain distribution. And then with that first frame, we take a measurement, y0, and then we would correct our estimate. And then we just keep iterating through this, right? So at every time t, we make a prediction for time t plus 1, take a measurement, and we correct for time t plus 1. And somebody spent a lot of time designing these beautiful arrows, so I wanted to make sure you saw them too. And if you go take a look all over the internet, you'll find these arrows. So now let's look at these steps one at a time. Let's first look at the prediction step, okay? So our prediction step is, given some belief about x at t minus 1, and given the measurements all the way up through t minus 1, make a prediction of xt, state at time t, still given only the measurements through time t minus 1. The way we do that, and it's going to be written out here in sort of a standard way, and then we're going to make specific use of that both, especially in particle filtering, which we'll do in a little bit. The way you would do that is what's known as, you use the law of total probability and marginalization, right? So the law of total probability and marginalization, I'm only supposed to be reminding you here, you're supposed to remember all your probability theory, right? That if I've got a joint density, right, P of A and B, if I integrate that over all the B's, what I'm left with is the density over A, right? That's marginalization. So what I'm going to do here is, the idea is, well, if I had a joint density of xt minus 1 and xt, and I were to integrate over all the xt minus 1s, I would just have the density over xt. So that's the marginalization. And the reason we do that is we can then break that integral up into the following, right? So you might remember the conditioning, right? Probability of A and B is the probability of A given B times the probability of B. That's what it says down here. So I've just broken up this integral down into this, where here's the probability of xt minus 1 given everything up through t minus 1, and I multiply that times the probability of xt given xt minus 1 and everything else. So I'm just applying the conditioning property to that integral. And then I can use that independence assumption that we said before. Remember, the independence assumption is that if I want the probability of xt and I'm given the previous state and a bunch of other things, those other things don't matter. The only thing that matters is that previous state. That's our dynamics model. So basically we have two things here. We have our belief about t minus 1 given everything up through t minus 1, and then we have our dynamics. Those are the two components that it takes in order to make that guess going forward. So now we know how to do a predicted value, right? So the p of xt given all our measurements. So given this, and then we take a measurement at time t. What do we want? We want the new corrected value, x of t given y's through yt. So we're folding in the new measurement, all right? The way we're going to do that is we're going to make use of Bayes' rule, and I have written down here for those of you who don't remember Bayes' rule and don't have it tattooed on the inside of your right thigh. But here basically is what we're doing, right? So Bayes' rule says that if I want to know the probability of A given B, I can flip it around by knowing the likelihood of B given A, and then there are these other terms in here, okay? And you'll notice what we did here is we switched this around. This is now the probability of getting the measurement given all this previous stuff times the probability. What is this? Well, that's just our prediction. Okay, that's P of A. And then this is going to turn out just to be a normalization factor. By using our independence assumption, right, the independence assumption says that our measurement yt given xt and all this stuff is only a function of xt, all right? And the reason that I refer to this bottom part as normalization is, remember, this is a probability over here, and basically they all have to sum to 1, and we'll get to that later, and this bottom value just normalizes everything so that it sums to 1. And if you really wanted to calculate that normalization, okay, what you have to do is you have to compute all the different possible probability of getting that yt over all of the xt predictions over the integral over all the xt. But we are never, ever going to be sort of computing that bottom part. That's just there so you can see what the sort of the total integral is. And in fact, now it says really a normalization. So it's really, really a normalization. So summarizing, we have two equations, a prediction equation and a correction equation. Our prediction basically takes two components. The estimate of our previous step, that is our belief about x after time t minus 1 was done. And then we have a dynamics model, right? And the way of thinking about this is the likelihood, the probability that x could be at some specific point. Well, it's the sum, or the integral, of getting to that point from any point that it might have been before, integrated over the likelihood that you were at those points before. This is a lot easier to see when we do the particle filtering where we make things discrete. But for the probabilistically inclined for you, if you look at that, you realize, remember we talked about marginalizing. What we're doing is we're saying all of the possible places we might have been before, what is the likelihood of it getting to some particular spot? And we have to weight that by all of the probabilities of having been at that point before. That's the likelihood of being at that next spot. And then you go to the next spot, and the next spot. That's the probability. That's your prior belief of your prediction about the places you might end up. P of xt given the measurements up until now. We don't have the measurement yet. Once we get a measurement, we can do a correction, right? And our correction we use doing Bayes' rule, right? We have the predicted value from before. That's the quantity we just talked about producing. And then we have an observation model. This observation model says, well, if you really were at some particular point, what's the likelihood of getting the measurement you just saw? And by using Bayes' rule, we use that to turn that into a prediction of xt given everything we saw, including, that's why it's in red, the new measurement. And then, like I said, on the bottom here is just the normalization. All right, well, that was painful. That's the mathematics behind sort of the general way of thinking about prediction and correction cycle of tracking. Fortunately, it gets a lot easier when we look at specific cases, specific models of how to do that. What we're going to do in the next one is look at a very simple analytic form of doing this called the Kalman filter. We'll show you the equations, we'll show you the update, we'll show you the intuition behind it without necessarily deriving the equations. Then what we're going to do is show you sort of a more modern approach using, it's referred to as particle filtering in computer vision, but basically it's this idea of using samples to represent densities. And when we do computing and vision, robotics, etc., the idea of using samples to represent densities gives us a lot of power because we're not limited to particular analytic distributions. So that will make those integrals either easier or even better, just simply go away. So let's do that next. So welcome back to computer vision. We're talking about doing tracking. Now, last time we introduced this idea of tracking as induction. That is, if I know what's going on at time t, or I have some belief about the state of the universe at time t, I make a prediction for time t plus 1. Then based upon that prediction, that might affect how I go get my measurement. I get my measurement, it's noisy, and I correct for t plus 1. And that continual loop, that's what we mean by tracking. And we did a little bit of sort of onerous mathematics where we talked about that the prediction part leveraged two things. It leveraged our belief of where we were the last time. That makes sense. And right, in terms of we might believe the position, we might believe the velocity or something. And we had to have a dynamics model. That is something that tells us about how things will change. All right? So given some belief about how things were and how things might change, that gives me a new belief about where things might be. And then the correction, the update after we took a measurement, remember we made use of Bayes' rule. And the idea is we take the prediction, we multiply that by a likelihood, and we'll talk more about that not so much today, but next time. And combining those and then normalizing allows us to know the prediction, our best guess now, of the state at time t after the measurement at time t. And that was referred to as the posterior distribution. So today we're going to do a specific case of what's called linear dynamics, all right, where the predictions are based upon a linear function of our current belief. And we're going to assume that we've got Gaussian noise both in terms of how things might change. So we have a distribution, we believe how things might change, plus there's some noise added, Gaussian noise. And furthermore, we're taking measurements, and our measurements are a function of the state plus noise. What kind of noise?
Gaussian noise.
Very good. And we'll show a simple linear recursive filter called the Kalman filter that's designed to handle this nice clean case. So what do we mean by a linear dynamics model? Well, it's pretty straightforward. A linear dynamics model says that our state at time t will be distributed according to a normal distribution whose mean is just a linear function of the previous belief. Okay, so D here is it's either a scalar or a matrix, depending upon whether X is a scalar or a vector. And then we take that and we put some Gaussian noise around it, some covariance. And by the way, you'll notice this little T here on these D's, okay? What that says is it could be that our dynamics model changes over time. That is, the actual multiplication that we do might change, but we assume we know it. So I'll tell you the vast majority of Kalman filters, those D's are constant, so that the transformation and this thing here, which is referred to as the process noise, is constant. All it's absolutely required is that it's known for every time t. So that's the linear dynamics model. We're going to do an example of that in just a minute. We also assume a linear measurement model, and that looks stunningly similar. All right, what that says is that the measurement we'll get will be some Gaussian normal distribution that's about some linear, M here is a measurement matrix, that linearly multiplies the state, and that the measurement noise is also a Gaussian. And again, it's subscripted by t because it could vary with time, but we assume that it's not. So what I haven't mentioned is that this x, both on this slide and this slide, those x's are unknown. We don't remember, it's the hidden state. We don't actually know what the state is. But we're saying is that this is how our linear dynamics model works. Let's look at a very simple one-dimensional example. Now that's not very exciting, but we've got our one-dimensional state. So x is where is this thing along some line. I may have state that says where it is. I might also have state about how fast it's moving. So here, what I'm showing you is a state vector that's both position and velocity. So here our state vector x is position. I'm using p for position instead of x because otherwise those x's would get too confusing. So we have p and v. What's v? Velocity. All right? Now, going way back to physics that you took in either 12th grade, 10th grade, 8th grade, or if you're really smart, 3rd grade, you learned some very simple update equations, right? That basically your belief about where the point would be at some time t would be wherever it was at t minus 1 plus delta t times whatever the velocity was, all right? That's just simple integration by velocity. And then you'll notice there's this little element here. That epsilon, that's noise. That says, oh, there's some noise that's been added, right? So maybe things aren't exactly perfect. Furthermore, I'm assuming that my velocity is constant, except that some noise gets added to that. That is, I might speed up or slow down a little bit, but it's totally random, and so I don't know anything about it, and so that's also going to be noise. Now, I can write these same set of equations in a very simple matrix form, okay? And here it is, that x at time t is dx plus noise, and here's this matrix, right? This is that matrix, 1 delta t 0, 1, which times the state vector, there's our state vector there, plus noise gives us what our next state vector will be. So this is a linear dynamics model where you're using position and velocity as your state. Now, what are we going to measure? Well, maybe we can only measure the position. So even though my state that I'm trying to estimate is position and velocity, maybe I only measure the position. I've got a little radar thing that pings out and says, oh, okay, I think this thing is about 2.4 meters away. All right? So that would be just a matrix of 1, 0 that multiplies the state, because all it does is it pulls out the position. And again, there's noise because there's noise in my measurement. Here's my M matrix, so this is the same linear model that I have for measurements. So I have a linear dynamics model and I have a linear measurement model. Now, by the way, I happen to be estimating position and velocity. I could also estimate acceleration, right? So here my state position, my state vector is position, velocity, and acceleration. All right, and I'm just including that to show you that that's a choice that you make as the model maker. You're going to build a model for doing this tracking, and this is what we're going to do. And again, I can write this out as a linear system using matrix notation, but now we have, instead of a 2 by 2 matrix, we have a 3 by 3 matrix, which includes the components having to do with acceleration. By the way, the other choice you also have when you do this, and I just mentioned this for completeness, is you can assume that there's noise in here or not. You can make those be 0 and just have the noise being the acceleration. It's not that you're assuming that your model is perfect, that is, that your estimates are perfect. You're just saying, well, I'm actually going to believe that the velocity, that this is how the position's really moving and this is how the velocity is really changing. And the only place that I'm putting in any change is in the acceleration. And you can do that either way. If you didn't understand what that meant, don't worry about it. Our measurement can still be the same. It can just be position only. And you might ask, well, if it's just position, how do you ever get velocity and acceleration? These equations that we'll set up will, when you sort of do the inverse to solve for things, it figures out that you have to take the differences between positions divided by delta time as velocity and the difference between velocities divided by delta time for acceleration, even if we're only measuring position. So it's time to introduce the Kalman filter. The Kalman filter is a method of tracking linear dynamical systems with Gaussian noise. And what's really cool is both the predicted states and the corrected states are Gaussians, right? So you're only maintaining the mean and the covariance of your state in order to run your filter. And also the calculations are very straightforward. I'm not even going to derive the equations here. We will get some intuitions, but you can show that it's a relatively straightforward manipulation of these linear matrices. So in pictures, the Kalman filter can be described as the following. All right, you start off in the blue here is at the top left. That's your prior belief, right? So let's suppose we have some density. Now, what kind of shape is it? It's a Gaussian. Why? Because this is a Kalman filter. Okay, Kalman filters are built on Gaussians. You want to have a non-Gaussian? Too bad. This is a Kalman filter. Things are Gaussians. We'll do some other little stuff later. For now, everything's. So the first thing that happens is, in this picture, is referred to as a deterministic shift. Remember when we multiply it by that linear system? So basically, that's the part that you know what happens. And that's shown here in green, where the Gaussian bump has just slid over to the right. So if I'm a Gaussian bump, which I've been accused of on a variety of times, the first thing that happens is I slide over to my right. That would be your left. Now, Megan is wondering, should I move the camera? I don't know what this guy's going to do. I'm going to come back in a minute. All right. Anyway, so the first thing we do is we slide. And we know that's the deterministic part. Then comes the part that's referred to in this picture, and I left it in here because I think it's a cool way of thinking about it, stochastic diffusion. But it's basically the addition of noise. And this is referred to the process noise. So now we've done two things. We've deterministically stepped one way, and we've grown a little fatter. Both problems. Anyway, the idea is when I'm taking a step forward in time, I use the part that I know. I think I was moving, 3 meters per second, and it's a second later, so I think I've moved 3. But I also know that I'm not perfect in my knowledge. Right? That's never my problem. That's somebody else. But no. Anyway, I know I'm not perfect in my knowledge. So therefore, over here, my variance is wider. Okay, so I've now expanded my uncertainty. Then what happens is I take a measurement, and that's shown here as Z. Okay, so I take some measurement, and what happens is if you take a look at the density in the blue here, you'll notice that it has shifted back a little bit based upon the Z, and it has also gotten narrower. Okay? It's very important to think about this in the Kalman sense, and we're going to do more of this in a minute, right? We shift, expand, measure, shrink. Okay? Actually, shift, expand, measure, correct, shrink. That shrinkage happens because whenever you take a measurement, you're getting new information. New information can only reduce your uncertainty. That's going to come back in a minute to be a little strange. I want to introduce, we're going to keep doing this Kalman filter now on the 1D state, and I want to introduce a little bit of nomenclature, some a way of writing things down. So what we have here is we have this inner loop that we talked about, where we predict, make a measurement, correct, and then time advances. Okay? So time advances, we predict, we make a measurement, we correct. The first thing I want to show is, in our prediction, which is probability of xt given the measurements up through t minus 1, our prediction in Kalman land here is going to be modeled, written as mu minus sigma minus, or sigma squared minus, right? This is, and see, of time t. So mu minus sub t, sigma squared or sigma minus sub t, that's the prediction of the mean and the covariance before I take the measurement at time t. That's why it's referred to as minus. Then I take my measurement, all right, and my corrected version, which is now the distribution of x given the new measurement y sub t, is referred to as mu plus sub t, sigma squared or sigma plus sub t. So I have these two things. I have mu minus, sigma minus at time t, that's the prediction before the measurement, mu plus, sigma plus at time t, that's my correction after I've taken my measurement. Let's go through the prediction and correction just a little bit in the Kalman 1D case. Remember, we're going to assume that the state at time t, okay, is just a constant times whatever the state was at t minus 1 plus some noise that's added, some process noise, right? So the first thing we would like to do is we would like to know our estimate. What's our best guess at time t given everything t minus 1 when we've got this Gaussian model? Well, we're going to write this the following, right? If something is a Gaussian and I multiply it by a constant, what does that become? It becomes another Gaussian. Or another way of saying it, I have some variable that's distributed by a Gaussian, and I multiply that variable by a constant, I get a new value out, but it's also a Gaussian, right? And in fact, if you remember from probability, right, its mean is just going to be that constant times the previous mean. So that's what this equation here says. This equation says that if I have my belief about the mean at time t minus 1 after I've done all my work at t minus 1, and if I believe that my dynamics are multiplying the state at every time step by d, my belief before I take a measurement about what the new mean is just going to be d times that. That's what this equation at the bottom says here, right? Mu minus at time t, the predicted mean, is just d times the mean from what I had before, okay? Because d is my multiplier. All right, so you remember that when I multiply something by a constant and it's Gaussian, the mean just multiplies. But what about the variance, okay? So now we have to update the variance. There are two things that are going on. First of all, we're taking some previous variable and we're multiplying it by a constant. That variable had some sigma squared to it. And maybe you remember, if you have a Gaussian, when you multiply that by a constant, its variance goes up by the square of that constant. So just in the multiplication part, all right, whatever the variance was before is going to go up by now d squared. But wait, we're not done. We also added in some more noise when we took that step, right, of d squared. So that means the new variance before we take a measurement is made up of two components. It's d squared times whatever the variance was before, so that's written as d sigma t minus 1 plus squared. Sigma t minus 1 plus is the standard deviation. If it's squared, it's the variance of what we had at the end of t minus 1. We're multiplying everything by d, so we multiply that variance by d squared. That's what this term over here is. And then we added in some more noise because of uncertainty of how the thing actually then moved. That is this d squared, okay? So even if we were multiplying by a 1, that is, even if we had no idea, there was, you know, everything was just a 1, our variance would still grow because of the added uncertainty, all right? So the update of the mean and the update of the variance for the Kalman is written like this, all right? What about the correction, okay? Well, the correction is a little complicated, so what I'm going to do is I'm going to show you the formula for it, then I'm going to give you the intuition behind it, then I'll show you, actually not the formula, I'm going to show you the simple formula for the 1D case, give you the intuition behind that, and then give you the full formula for the ND case. First, remember that we're assuming our measurements are, again, just some constant times the actual state plus some Gaussian noise. Okay, that's our linear system plus Gaussian noise for the Kalman filter. Remember, we have our predicted state. We just did that. We said that that's mu sub t minus, right? That's the predicted mean. And then sigma t minus squared, that's the variance of the prediction. And what we want is we want the corrected estimated distribution. That's what this is here, all right? So in Kalman, with linear Gaussian dynamics and Gaussian measurements, the corrected distribution is defined to be, I'll show you that, a new Gaussian, okay, which is now mu t plus and sigma t squared plus, all right? And what I want to do is I want to show you the formula for that and then give you the intuition behind it, okay? This is the formula for the mean, okay, so here is mu t plus, and it's a combination of mu t and the y, which we'll get to in just a minute. The update of the variance is here, so sigma t plus squared, okay? And you'll notice that what's happening is that this number, if you just do a little bit of this math here, is actually going to end up being smaller, okay, than the predicted variance. And that makes sense. Why? Because remember, after we take a measurement, our variance goes down. So let's take a look at the mean. This one will be a little bit more clear, all right? So this is the equation just copied from the previous slide to this slide, all right, for mu plus. Step with me. I'm going to divide by m squared, okay? So when I divide by m squared, okay, so you see I've just divided by m squared, so there's an m squared down here, and this m becomes m there, and this becomes an m squared there. Okay? Cool. So what is that?
I have no idea.
Well, yes, you do. Here it is. Look, see this yt over m? Remember, y, the measurement, was just m times x. So yt over m, that's the measurement's guess of what x is, right? If you were looking just at the measurement, that's its guess. Now, mu t minus, what's that? What mu t minus is, that was our prediction, right? That's the mean. That's our best guess as to what x actually is at time t. Okay? So we've got these two things in here, right? We've got mu t, which is our prediction, and y over m, which is our measurement's guess. We have to somehow combine them. Well, how do we combine them? Well, what's this value, right? This is just sigma squared divided by m squared. That is the measurement's variance divided by m squared. That's the variance if you were to compute x just from the measurement. So this guy right here, that's the x computed just from the measurement. The variance of that is sigma squared m over m squared, because y was just mx. All right? So that quantity right there, circled in blue, that's the variance of x computed from the measurement. And what is the last term there? Sigma t minus squared, that's the variance of the prediction. And you might say, well, so what?
So what?
What do you mean, so what? No. What this means is that the entire mu t plus is just the average. It's a weighted average of the prediction and the best guess based upon the measurement. And so down here in the denominator, that's just the sum of the weights. It is just a weighted average of the prediction plus what the measurement is telling you, which of course is what, in some sense, the universe has to be, right? The whole idea is you're making a prediction, you're getting a measurement. Both of these are sources of information, and you want to integrate them. In fact, we can take a look at that a little more carefully, all right? So here are the expressions that we have before for the new mean and the new covariance. Suppose there's no uncertainty prediction. What that means is that sigma t minus equals 0. I don't know how that would have happened, but let's suppose you just know where this thing is. So then what happens is if this is 0, okay, gee, let's take a look over here. Then this thing is 0 here, this thing is 0 here, this thing cancels out. What it means is that your best update is the one that just uses the prediction, because you knew exactly where it was going to go. And furthermore, your new covariance is 0. That is, you have no uncertainty. Another way of saying this is your measurement is ignored. Okay, so if I'm sure of my prediction, I should ignore my measurement. Likewise, what if there's no measurement uncertainty? Suppose your measurement's perfect. What should you do? Well, if you plug sigma m equal to 0 in here, you'll see that mu t plus, your new best guess, is just the measurement divided by m. That is, it's just the measurement's guess as to what x is. You're totally ignoring the prediction. And this is what Kalman does for you, right? It gives you this trade-off between how much you pay attention to the prediction versus how much you pay attention to the measurement as a function of the uncertainty of the prediction and the uncertainty of the measurement. And that's what makes it so powerful. All right, now I'm going to make some simple changes with A and B, right? So A is here, and A is just this quantity there, and B is here, and B is just this quantity there, in which case this whole expression, I replace the A and B, keep going, again A and B, carry it forward. Here what you'll notice I've done is I took A here, I added in the B there, which ends up subtracting that there, keep going, and what you'll see is this expression that says mu t plus, our new belief after we've taken our measurement, is just mu t minus. What's mu t minus? Mu t minus was the prediction, and then we have to change that prediction a little bit, and that prediction is changed based upon two things. The first thing is based upon this difference here. What's that difference? That difference is the residual, right? Y divided by m, that's the measurement's guess, right? That's the measurement's guess of x. Mu t minus was your prediction. The difference between them is the residual. And I multiply that by some factor k, and that k is called the Kalman gain. If my Kalman gain was 0, then I ignore my measurements altogether and I just go with my prediction, okay? If my Kalman gain was 1, let's see, I put mu t minus mu, I ignore my predictions altogether and I just get my measurement. And it's that Kalman gain that you're estimating that goes between essentially 0 to 1 in the scalar case and does something funkier in the multidimensional case. All right, let me show you that in a simple example. And this is going to be a constant velocity model. And what we mean by that is we assume that the velocity is constant except a little bit of noise. So the state is two-dimensional. It's the position and the velocity, right? So it's I'm moving in one dimension, but my state is two-dimensional because it's the position and the velocity. And now we're going to take a look at this graph, all right? So in this graph, all right, so we have time and position as the things we're measuring and the thing we're estimating. The red line here is the state. This, we happen to know, was the actual underlying state, okay? How did we know this? We booked a trip to Delphi. You know where Delphi is? It's in Greece. They have a thing there called the Oracle. They also sell really good baklava, but that's besides the point. You go to the Oracle, and the Oracle tells you the truth, okay? It tells you whether the Mets will win the World Series. They always say no. And they also tell you the state. But the idea is, for the point here, I'm just showing you the graph. That's the actual state. But we also took some measurements, okay? And the green dashed line, these are the measurements we happen to get. Now, you'll notice pretty crummy measurements, right? Life is the way life is. This is the noise that we actually happen to get. The purple line here is the corrected mean, okay? And what you're seeing here is that the mean is sort of being pulled around, the estimate, all right, is being pulled around by the measurements, but you see that it tracks the real state much better than the measurements do, right? Because it's blending a prediction where it's estimating the velocity with the ability to incorporate the measurements. If you want to take a look at the error bars here a little bit, one of the things that's cool, in fact, I'll look at just the last one, right? This was the error bar of our prediction. Okay, so remember, see it says the predicted mean, which is right there. And then after we did the Kalman filtering, this was our new guess, all right? And our error bars got smaller, okay? So again, this is what's happening is we take a step, we get bigger, we take a measurement, we move, and we get smaller. What I just showed you were the formula for the one-dimensional case. We almost always do this in the n-dimensional, because even when we were having x move in just one direction, we had a two-dimensional vector of position and velocity. In the two-dimensional case, these are the Kalman equations, okay? We have our state vector x. We assume our prediction is just based upon a linear transformation. Our covariance prediction, or the covariance of the prediction, this is that squaring operator. Remember before we did d squared sigma? Well, when you're doing this in matrices, it's d times the old sigma times d transpose. That's the squaring. Plus you add in the noise, the process noise. So those are your prediction measurements. And then your correction looks like the things on the right. The thing for you to notice here is, you see the quantity in the green box? This is the residual right there. And you're multiplying it by this Kalman gain matrix, all right? And the Kalman gain matrix has less weight on the residual as the prior covariance estimate approaches 0. So as this value's, it's hard to say what it means for covariance to go to 0, but let's talk about its trace. But the idea is that it's getting smaller. As it gets smaller, the Kalman gain goes down, which is what you want to have happen, right? If your covariance of your prediction is very tight, I don't want to pay a lot of attention to my measurement, so I don't want to weight the residuals very much. On the other hand, if my measurement covariance goes down, okay, so now what happens is this value is very small, which means this value is what's getting put in the inverse, right? So now this sigma t goes away. What happens is the Kalman gain matrix goes up, its magnitude, if you will, goes up, and it weights the measurements more. So these matrix equations are doing exactly the same thing as the scalar equation did of balancing the prediction and the measurement. There's a really nice little graphical illustration of tracking with Kalman filters. So let's suppose we have some current estimate of where we think things are, right? And that's what's represented by this little circle here in the xy plane. Our prediction shifts and grows, and that's why the size, if you will, and you can think of this as being a single, say, some number of standard deviations of uncertainty. So our uncertainty matrix got significantly bigger, and the mean may have shifted as well as also, so that's our prediction. We then take a measurement, and you'll notice that the measurement here is offset a little bit. I mean, and it happens, you know, its mean is right in the middle, and it's actually tighter. So it actually has a tighter covariance than the prediction, okay? But the thing that's important to realize is the correction has a tighter covariance than either one of them. So you'll see that the mean of the final correction is somewhere between the mean of the measurement and the mean of the prediction. Remember, it's going to be a weighting between them. And also notice that the covariance of the final corrected estimate is smaller than either of the two, all right? And this might seem a little weird when you look just at, say, the covariance of the measurement and the covariance of the prediction, because they're both pretty big. And you might ask, how is it that the covariance goes down even tighter than the measurement? And again, the answer is information can only reduce your uncertainty. So whether you think of as measurement as reducing your uncertainty about the prediction, or the prediction is reducing the uncertainty about the measurement, what that means is your final covariance will be less. You'd be amazed at the number of PhD qualifying students who, when asked that question standing in front of the board, kind of flump through it. So if you're thinking about doing a PhD, and I'm going to be on your qualifying committee, and you're doing something in robotics, get to know and love your Kalman filters. This can be seen sort of simply in this 1D case. So we start off with a prior, and here it is as a Gaussian. We have some measurement, that's the evidence, and here it happens to be tighter. And then we get a posterior, right? And the posterior is narrower, and because it's narrower, it's also going to be taller. And then the prediction step, we just take that posterior, and we do the shift, and we grow the uncertainty again. So far, everything looks like it's behaving really well. So let me give you a quiz. Well, it's not a real quiz. It's like a fake quiz, all right? Suppose this is your prior, okay? Okay, so you see it's this nice white Gaussian lump over here. And then suppose this is your measurement, okay, this nice tight green. Where does the posterior go? Well, first of all, it's got to go somewhere in between, because in Kalman filtering, your mean is a weighted average between the prior's mean and the measurement, okay? So the fact that it's going to go in the middle is okay. But what might bug you is it's got, again, that tight little uncertainty. I got this Gaussian bump here, all right? Now, Gaussians go to 0 really, really fast. So by the time we get out here, it's like incredibly unlikely. But then all of a sudden there's a measurement bump over here, okay? So, you know, what's poor Kalman to do? Well, Kalman has to put them somewhere in the middle because that's all it does. And furthermore, it has to reduce that uncertainty because it's a slave to its model. it really, honest to God, believes that things are distributed by these Gaussians. And if they really were, then that's the correct value to put in. And the question is, does this agree with your intuition? And the short answer should be, I don't think so. Because, Megan, over here, okay? If I've really got a Gaussian lump over here, then the idea that something will now be over here, the probability is so infinitesimally small that what's probably the problem is that our model is wrong. We really should be trying to abandon the model at that point as opposed to doing the integration. And in some sense, that's the part of the message of Kalman filter. You're actually a slave to the model. You really believe it. So reviewing it, sort of the pros and cons. What's the biggest pro of a Kalman filter? It's all listed here as one, but look, it's just very simple. You know those equations, you just implement them, you write them, it's compact, it's efficient, it works pretty well. You have to sometimes tune some things, like you never want to let your process noise get too small. It's much better to overestimate process noise than under. Why? Because if you, for example, suppose you didn't think there was any process noise at all. You thought this point is just there, okay? So you're taking measurements. Well, if there's no process noise, remember, every time you take a measurement, your uncertainty goes down. Eventually, you'll go to an uncertainty of 0, and you'll stop listening to your measurements. So it's always good to have a little bit of process noise. So there's some tuning to make it work, but in general, it's pretty clean. The biggest problems with it are that it's, first of all, fundamentally a unimodal distribution, right? I've basically got a Gaussian, which means I basically have a single hypothesis, right? And it's some uncertainty within that hypothesis. There are some other issues here. Remember, we have this linear model. There are ways of fixing that. There's something called the extended Kalman filter, which basically just takes, for those of you who care, you linearize about your current point. That's like taking a Jacobian around a nonlinear system. You currently estimate it linearly, update, then recompute your equations in the nonlinear prediction. So the linearity part is not that big of a problem. But this problem of having a single hypothesis, okay, that's a Gaussian, that doesn't work so well sometimes. So the question is, what should you do if the world's not Gaussian or it's not even unimodal? And the answer is, you should come back next time, because we'll tell you then. Welcome back to Computer Vision. Today we're going to continue on our long and winding excursion through tracking. And in particular, what we're going to do today is we're going to revisit the whole notion of Bayes-based filter tracking or Bayesian tracking. And sort of develop a method that allows us to do that well. So you remember the tracking with dynamics, right? So the whole idea was, because we're tracking something that's moving with respect to the imagery, we're going to learn something about the dynamics and use the dynamics in order to make predictions. And we're doing this so that we can limit the area of search that we're looking in, and also so that we can get a better total estimate when we're done, under the assumption that the things we were trying to track, you can't perfectly detect them, and it's noisy to begin with. And we're basically making an assumption that there's some sort of smooth motion going on, and that essentially our dynamics don't surprise us is the underlying element. So last time we developed what was called the Kalman filter. And the Kalman filter was for linear dynamic systems, where you had Gaussian noise context. So what we meant by that was the motion could be predicted by a linear factor applied to the motion that you've estimated, and then you add in some Gaussian noise if you were thinking about what the uncertainties are. Same thing with our measurements. They were a linear function of the state, and then there was some noise. And what was nice about it is everything, prediction, correction, your lunch break, it's all Gaussian. All right? And so the only thing you have to do is maintain the mean and the covariances of these Gaussians. And it just works in 1D or ND, et cetera. It's real easy. And the calculations are pretty straightforward also. I mean, the equations looked a little ugly, but it's just a bunch of matrix multiplies and a couple of inverses. Pictorially, the Kalman filter looks like this. Nice Gaussian. I don't know why I'm drawing this. It's already here. A Gaussian. I'll circle it. We start off with that Gaussian. We then have the linear prediction part, which does the shift. We then say, but wait a minute, there may be some noise, so things get widened. We take our measurement and we sort of blend. Remember, it was that the Kalman filter is a blending between your prediction, which was what our prediction here was, and your measurement, and it creates a new estimate that's a weighted average between those depending upon the relative uncertainties. And the uncertainty gets smaller after we take the measurement. So uncertainty gets bigger when we do our prediction because we don't know exactly what happened, and then it gets smaller again when we take the measurement. We said nice things about it was that it's simple, it's compact, it's efficient, and it's very easy to spell. The cons of it are, in fact, maybe I should have listed these in the other order. Here it says, we'll say there's sort of a restricted class of motions defined by the linear model. The linear thing we can get around by using what's called an extended Kalman filter. A much bigger problem is it's got this nice unimodal distribution assumption. You're assuming the world really is a nice Gaussian of some uncertainty. And the question arises, what would you do if things are not a Gaussian? So what's an example of when you might need a non-Gaussian situation? Well, you remember these videos? Okay, and again, this comes from the Izard and Blake condensation tracking paper. There's all sorts of dynamics going on here of things jumping around. Let's see if I do that again. Yeah, there she goes. And things move quickly. They may be able to be nice and smooth sometimes. Then something rapid will happen. So like when the leaves are blowing in the wind, for a while they blow nicely. But basically, the problem here is that things are moving smoothly, and then all of a sudden you'll get a perturbation. And you'd like to be able to keep track of that. So graphically, we're going to show that like this, okay? So now we have the same model that we had before, okay? We have an estimate from the last time. We have a deterministic shift. We apply some smoothing because we grow the uncertainty, and then we take our measurement and we update our estimate. But now these are not Gaussian lumps, right? These are sort of arbitrary distributions. And in fact, this particular figure is taken from the paper that introduced the particle filtering that we'll talk about in a minute to computer vision, that condensation paper I just mentioned. Before we go any further, just something you should know. In particle filtering, the measurements are typically referred to as the z's, z sub t, and not as y of t. It was just the way it was done. It has to do with whether you're connected to vision or robotics. In order so that it aligns with various papers and other formulations you'll see, we're going to start showing Z's in the slides to come. It also made it much easier to borrow slides from other people because they were using the Z's. All right, so the key to sort of particle filtering is the following. If we have a distribution, and here we have a nice little distribution, which you see is, I don't know what that distribution is, but I know one thing. It's not Gaussian. Now, somebody who's really smart out there might say, well, it looks to me like a mixture of Gaussians.
Well, it sort of looks to me like a mixture of Gaussians.
Yeah, in this particular case, maybe it is. That's just for convenience of drawing. And in fact, there is a relationship between mixtures of Gaussians and particle filters, which we won't even talk about. But basically, the idea is you have a bunch of things which together represent your density. In particle filters, or sample-based methods, what you have is you have a set of particles. And here the particles are drawn out where you can see these particles. It says xt. That means these happen to be our particles at time t. And there's n of them, and the bigger n is the better. And you'll notice it says weighted here in parentheses, because sometimes they're weighted or sometimes they all have the same weight. The density is represented by sort of where the particles are. So you see we have a nice high density here. So we got lots and lots of particles there. Okay? Not so many particles here, not so many here, and lots of them there. All right? So that's where they are. And if they were weighted, it would be as if you can think of that as having two particles in the same spot. If I had double the weight, it would be like having two particles at the same spot. And now you can say that the probability density that x is some value is essentially the probability, if you were to draw out a particle, that you would get a particle whose value is really, really close to that spot. Okay, and that's what it means to use samples or particles to represent a particular density. And if you're doing that, then your overall goal is you want, sort of as n gets bigger, the idea is that the probability of getting a point from this distribution, that's x as an element of xt, is approximately what the underlying probability was. And for tracking, the idea is given everything we've observed so far. So what are our observations? Remember, they're z's. So given everything that we've observed so far, what's our belief about where x is, and we want to end up with a set of particles that gives us that density. We still have to do the same things we had before. So you remember when we were doing tracking, we had this notion of a dynamics model. For Kalman, it was a linear model. So the idea is that at each time step, we have some prediction that allows us to say, well, if I have some density about where I think I am, what's my new density? And in that particular case, it had to be linear in order to make the math work out. That was, the underlying part of the Kalman. All right. But in general, we can have a more general state transition matrix, right? So the idea is that what is the expected change from time t to t plus 1? Okay, so if I'm at some point, or if I'm guessing that I'm at some point, I could say, what's my expected change? So what's important about this, and the reason I'm going on and on about this, is besides just having sort of a dynamics model that says how things are likely to evolve, I can also include a notion of perturbation or control. All right? So the perturbation means if I was here, maybe I know that I took 2 steps to the right. Now Megan's freaking out again. All right, I'm back. All right? So what I would do is I would say that, okay, the expected state transition is that I take where I am, I take 2 steps to the right, and then I add some noise. So it's a little bit like, remember we talked about that in the linear model? I could actually have a different linear transition at every time t, but usually we keep them constant. Here, we're going to have the notion of an input, and the input is represented as u. U for input. Don't ask me. If you want to know why, ask some control theory professor, because they always use u as the inputs or as the desired. Anyway, so we're going to see a u sub t. That's the control or the input or the perturbation that got added to the system at time t. And we assume that we know that. All right? So what we've done is we've changed our filtering just a little bit so that besides just taking observations, we're going to assume we have observations plus assume that we have we know what the inputs are. All right? Lots of words, but I hope you follow that.
Now, why would you want to add perturbations to a model? Isn't that what noise is for? Let's consider a real-life scenario. Let's say I am a robot ambling away on the moon. My goal is to reach this flag. I can use my camera to detect and track the flag. This is what my view of the world looks like. Now, where the flag shows up in my view and how it moves depends on a bunch of different things. For instance, my movement across the surface, both back and forth and turns. Now, the surface is really bumpy. This can cause my view to shake quite a bit. I can also move my camera independently, pan, and tilt. The most annoying is probably the wind blowing the flag all over. It really messes up the appearance. So which of these are known perturbations that we can model for? Okay, this was fairly easy. When we're moving, we know how we're moving. That is, we know how our view of the world should change with the movement. Therefore, we can take it into account in our model. Same goes with turning the camera. Now, perturbations caused by the terrain or wind are things that we cannot explicitly model for. We still know that they can affect what we see, so it's probably a good idea to include it in our noise model. Known perturbations, or control inputs or actions, allow us to build in phenomena that we can explicitly model for.
So we're going to go over a Bayes filter framework, and so given 4 things. First is, I'm going to need some prior belief about where I'm starting. Okay, so that's P of x. Where did that come from? Again, remember that drive up to Delphi and asking the oracle and all that stuff? So you forgot your luggage, so you went back to Delphi, you got another prior, and it tells you how things are starting. But again, maybe with a large uncertainty. So here we have our dynamical system model, and so it's the probability of some new x given my belief about the previous x plus this input. By the way, you see here it says u sub t minus 1. The world is sometimes schizophrenic about whether you think of the input as happening just after the last measurement, so it was u at t minus 1, or u happened now and I want to estimate what the state is now. So whether it's ut or ut minus 1, it's whatever you're going to add on to xt minus 1 in order to make your prediction about xt. All right? So we're given these two things. We're given a prior and action model. We're also given a sensor model. And this is going to be really important, a little bit important this lesson, very important next lesson. And the sensor model is our likelihood, okay? And it is not, I'm going to tell you what it isn't first. It is not, given some sensor reading, where do I think the object is? You might think that's what it is, but then you would be thinking incorrectly. No. A likelihood model is, if the object were really someplace, what's the likelihood of my measurement? So normally what you'll see is, and we're going to see some later, like a little Gaussian blob drawn over the place where the measurement was. That does not mean, okay, that given this measurement, this is my distribution of where things are. No, no, no. What it means is, this is my likelihood, so it's highest if x was actually at this point, and then it falls off slowly. All right? That's the likelihood. And then finally, we're given the stream of observations, the z's, so z1 through zt minus 1, or through zt. And also, we know the actions, okay? So we know the action data u1 through t minus 1, okay? So those are the four things that we have, all right? What do we want? Well, what we want is the estimate of x at time t. Okay? Same thing we've always wanted since we were little children. And in the Bayesian world, this is called the belief or the posterior of the state, right? And so sometimes it's even written like this, BEL, for belief of xt. What's my belief about xt given everything that I've observed so far, knowing all the perturbations, and given my current measurement?
I'm still a little fuzzy on this likelihood thing. Let's jump back to the moon. Did I tell you about my star sensor? I use it to navigate around. There are hardly any other landmarks. When I point it to a region in the sky, it says bright star. That is, if there is a bright star in that region. If I told you that I was looking at this particular region in the sky, how likely is it that my star sensor would go off and say bright star? Choose the appropriate radio button underneath on a 3-point scale, from least to most likely. Now do the same for these other regions in the sky. Remember that I'm asking you to estimate the likelihood P of bright star given the sky region. Okay, the first one is very likely. Second and third, not so much. Last one, maybe. Okay. So the distribution of P bright star given sky region looks something like this. Remember that this is not enough to give me a definitive answer of which region I'm looking at. I need to combine this with my prior probability of where I think I'm looking. This would come from my previous estimation step or just be a random distribution in the beginning.
A couple of more things about the model that are similar to what we did before for the Kalman, okay? Since I know some of you have a machine learning background a little bit, drawn here is a graphical model. The idea is that x is only impacted by what the x was before and what the new perturbation is, and the z's, the measurements, are only a function of the current state. All right? And that's written in the following way, right? The first thing says the probability of the measurement, given all the states, given all my history, is only a function of the current state, and that's sometimes called sensor independence. Okay, the sensing is only dependent on the current state. All right. The other element is this one that says the probability of the next state, given all of these things that came in and including the states before, is only a function of where we were before plus the current input. And by the way, here, this is written as ut, not the ut minus 1. That's what I was telling you about before. It's shame on me because I did both of these and I should have made them consistent. But the idea, this is the Markovian property, right? We had the Markovian property last time also. The Markovian property says if I know the state at the last time, none of the earlier state information, none of the earlier measurements, none of the earlier anything matter except the state then, and then the one thing we've added new this time is action at the current time, okay? That's the Markovian property. So before we go further, I'll just remind you again of Bayes' rule. We looked at this last time. The straight Bayes' rule is that we can say that P of x given z, the P of the state given the measurement, can be written this way. This is the likelihood, all right? This is the total probability of z. That's our prior before the measurement. That's our belief, if you will, of what the value was, okay? So what's important here to realize is once I get the measurement, somebody gives you the measurement. You drove to Measurements R Us and you picked up your measurement. You didn't know which measurement they were going to give you, and there's a probability that they'll give you all these different Once they give you a measurement, the probability of having gotten that measurement is done. It is whatever it was. It's not going to change. So what that allows us to do is to sort of replace that by this normalization factor, right? It's some value. Or another way of saying this is that P of x given z is proportional to P of z given x, all right, times the prior. So if I had a whole bunch of different possible x's and I only had this value, okay, for P of x given z, they have to sum to 1. So what I could do is I could just take the sum of all of those, whatever they were, and then divide this value by that, divide by that sum, and I would be back to a renormalized probability density, all right? That's why we write it as this eta, we talk about this proportion. And in fact, next time when we do particle filtering, you'll see that what we do is we sample all these x's, we multiply them by their likelihoods, and we get all these values, but they don't sum to 1. So what we have to do is take all the sum them up, then divide each of those by that sum, and they'll sum up to 1 again. What I want to do is work through the slides here on the Bayes filter, getting us to how we come up with our new belief, okay? So this was just our definition before, that the belief is the probability about the current state, given everything, including the current measurement. So we're going to use the Bayes rule that we just showed that says we can swap that around by putting in the likelihood and the prior. And the prior is just xt without the zt over here, right? That was our prediction about what xt was. And this is this likelihood model, right? This is just our sensor likelihood model. What's the likelihood of getting that value? All right? Well, our sensor independence that we talked about before says if you have the state xt, then none of this stuff matters, and it's just P of zt given xt. That's sensor independence. All right, so here we are. So the next thing we can do is, remember we talked about this before, this notion of total probability. The way we do a prediction, okay, for any given xt, what we have to do is say, well, what's our prediction of all the possible xt minus 1s? And why are there many of them? Well, all the possible x's at t minus 1. If we take all the probability, okay, that we sum up over all those possibilities, and here you notice what we said was what's the probability of going to xt from xt minus 1 times this probability of xt minus 1 summed up over all of those xt minus 1s. That will be the prediction. That will be the prior. But this value actually can get made much smaller because notice that it has this term and that term. Because remember, the Markovian property says that if we have xt minus 1 and we want to predict xt, all this other stuff doesn't matter except the action, right? So basically, if you give me where I thought I was before and what action you did, I can tell you about where I think I am now. And that's what this Markovian step is right there. One more time, flies up. Wow, beautiful. Okay, keep going. All right. Well, now actually we're pretty much done. And now everything is beautiful and color-coded. All right. We start here, right? This value right here, that's just our belief about all the x's at the last time step. So that's written here. So now we're already looking at a recursive algorithm, right? Because on the left-hand side, we have the belief of xt. On the right-hand side, we have the belief of xt minus 1. So this is a induction. Remember we talked about tracking as induction. This is an induction formula that goes from your belief at t minus 1 to your belief at t. when you integrate or sum over all the possible xt minus 1s, these are your predictions before taking the measurement. So this is just like we did with the Kalman before. To make your predictions, what you do is you take your belief about where things were, you pump it through your dynamics, and you add it onto your uncertainty. And then what this is showing is, to get our new belief, okay, we just multiply that by the likelihood of the measurement. Remember, it's not your probability of where you are given the measurement. It's how likely would this measurement have been if that had been the particular x. And then we can worry about this normalization later. That's how we get the belief at new time t. We're going to stop here for a little bit, let you catch your breath. Go back, review, have a beverage of your choice. Make sure you understand this. Or just complain that, gee, this seems redundant with what we did right before the Kalman filter. Because, yes, the math is quite similar. In fact, underneath it's identical, but what we're doing is we're moving to get to this notion of a normalized Bayes rule application as opposed to the straight Kalman. And then what we're going to do is we're going to use that particle representation that I showed you before to do this, and it'll all become much clearer, I hope. All right, welcome back to Computer Vision. We're going to continue introducing particle filters for tracking. I also want to say thank you. I think it's Sebastian Thrun and/or Dieter Fox or somebody else who's done a bunch of slides that have actually lost, their authorship is lost to all of humanity, because if you take a look at particle filtering, you'll see these same pictures everywhere. So whoever did them, thanks. All right. So you remember, I hope, that the reason we're doing all this is because, unlike Kalman filter, where we were going to represent the densities to where things are with a nice Gaussian, the idea is we might want to have an arbitrary density. And graphically, that's what's shown here, the idea of propagating a density through time. Now, the basic idea that we're going to make use of is, instead of having some sort of analytic representation of our densities, we're going to have these set of particles. We talked before about how the distribution in terms of where the particles are and perhaps the weight of the particles, that's what we're going to substitute for the density, right? And our goal is so that as we're doing this tracking, eventually we have a set of particles such that the probability that you get a particle at some particular place is essentially the probability that the state is actually at that place, having observed all the observations. And the way we do this is we're going to do this as a Bayes filter. We introduced this last time, where we said that basically you take your prediction from before, and the way you get to your prediction is you take your previous belief of all the different places you might be and talk about the probability that you could end up at some given xt. You sum that all up, and that's your prior belief that you could be at xt. You take your measurement, you multiply it by your likelihood, and because of Bayes' rule, which does the swapping of the variables, that gives us our new belief about xt. So we're going to take particles, and we're going to define a Bayes filter using those particles. We're going to illustrate this with a very simple example, and here it is. So imagine you've got a robot that just has two things, okay? It is a map of a hallway, okay? So here you're seeing a hallway. And by the way, this little blue dot here, this is the robot. The robot doesn't actually know where it is. We know where it is because we're really, really smart, okay? Or we work for the NSA. I hope that didn't cost me my grant. Anyway, so the robot knows this map, and it knows essentially where the walls are and where the doors are. And we'll assume that the doors are open, right? The other thing that the robot has is it just has a detector, a sensor, really dumb, that just looks out to the side. You can even think of it as it's just got a stick, and it pokes it, and it says, do I hit something or don't I? And by the way, it's not very accurate. So he sticks it out there, and sometimes he sticks it this way, and sometimes so it's approximately that direction. He just says, did I hit something or not? Now, you might think that would be an incredibly dumb robot, and you might be right, except here's a picture of a robot. I don't want to insult my SRI friends, because this robot actually got pretty smart. But this is the robot originally Flaky here. And Flaky had down below on the bottom these little ultrasonic sensors that would send out a chirp, and it would respond back, did I hit anything? Or how far away was the thing that I hit? So humor me that this is just a robot that basically detects just a hole or just not a hole. That's the only thing that it knows. And because it's not perfect in setting out its signal, right? Just because it says the sensor says hole doesn't mean it actually was a hole, right? And just because it says wall doesn't mean it actually was a wall, okay? So this example, this robot that's going down the hall, it's got this noisy sensor, this is perfect for sort of a probabilistic Bayesian filter-based tracker. And the reason is, first of all, it's going to have some continuous belief about where it thinks it might be, right? So that's its belief, its distribution, its posterior about where it thinks. And its measurements are noisy. And furthermore, it's really unlikely that, depending upon its measurements, that it will have a nice Gaussian belief about where things are. Its belief is going to be whatever it is. So we're going to make use of a particle filter to do this. All right? What you're seeing here is this is the prior density. So here's our little, should we name our robot? Sure. What's a good name? See, I would use some like R2-D2 kind of name, but then I would get sued by George Lucas. So we'll call it R3-D3. Okay, so R3-D3 is sitting over here. And this here, this is its prior belief about where it is right now. We have no idea how it got that value. This is its random distribution. And you can see it's a pretty uniform distribution of particles. Now the sensor reaches out and it gets a measurement. And let's just suppose it sticks its stick out and it sees a hole. What that means is the stick doesn't run into anything. So it says, it's a hole. Now, using the sensor model, the robot has to evaluate not where it thinks it is, but first, what's the probability that I would see a hole if I was at each of these locations? So after the robot sees the hole, what it has to evaluate is, what is the likelihood that I would have seen a hole if I was at this location? So these values here, these are not the probability that I'm at that location given that I saw a hole. It's the probability that I would see a hole given that I was at that location. So the reason that it's highest in the middle is because even if I've got a wiggly stick over here, the likelihood that I see a hole is higher than if I'm sort of at the edge of the hole, right? Because then I might sometimes run into the wall, sometimes run into the hole. And that's why I have this nice tight little distribution like that, okay? So remember, that's not P of x given the hole. It's probably that I would see a hole given that I was an x. Then what do? Well, in our particle filter, we just multiply P of z given x, probability of the hole given x, times my prior distribution for every one of these x's, okay? So that's what this distribution is down here. That is the multiplication of the prior times the likelihood. And in math, remember, the belief is proportional to the prediction, or my belief prior, that's this here, times my likelihood. That's this value here. And then I have to normalize the whole thing in order to get a new belief. Okay? That's why I'm doing that. So, what happens on the next step? All right? Well, the first thing that happens is we resample. By the way, we're going to go through the exact algorithm of this in a little bit. To resample, what we do is we first randomly pick a particle from this top distribution. This is the distribution we had after the multiplication, right? And, of course, the bigger the weight, the more likely we'll pull out a particle. That's what these weights mean. So we're more likely to find things here than, say, over here for two reasons. One, there's just more particles over here than over here, or to the right than on the left. And also those particles have a higher weight. They have a bigger value. So I sample the particles, and every new particle that I create starts off with a uniform weight. So I just, let's say I need 1,000 particles, 1,000 times. I might get the same particle more than once. That's okay. Then what I do is I sample and I move. Now what do you mean move? Well, remember those actions, the U's? Okay? So if the robot thinks it took a step 2 meters to the right, okay, it shifts that particle by 2 meters. It shifts its belief of where it is 2 meters. And then finally, it adds a little bit of noise. This is just like we were doing with the Kalman. Remember, you start off with the distribution, you do the deterministic shift, and then you add some noise. Well, to do our distribution, we first have to sample our particles. then do the deterministic shift, then we add a little bit of uncertainty to that. Okay, so here you can see the resulting thing is we have a density that has been resampled, so there's like a whole bunch of points, and shifted with a little uncertainty added in. Now I take another sensor reading. By the way, I just copied over, see the density on the bottom? I just copied over. That's the belief that the robot has. The robot sees another hole. So that means P of Z given X is the same thing I had before, because I got the same reading I had before. I saw a hole. So, and again, I multiply, but this time I multiply the previous density by this, and you'll notice now that the robot has a lot of belief, okay, that it's actually where it really is. And the reason is it saw a hole, it took a meter, it took a step of 2 meters, saw another hole. Megan's really hoping I don't go another 2 meters. I won't. And just that amount of information is enough for it to have a pretty good belief about where it is, okay? There's still some probability that it's over here, because if that previous reading was just wrong and the current reading was right, then I might be there. Same over here. If the current reading was right, but the previous reading was wrong. No, the other way around. Anyway, the idea is that it's weighting these different probabilities, okay? And you could, do it again, so you resample and you move, and you see here we have the resample density where most of its belief is in the right place, and there's some densities there, and that's it. And that's the way a particle filter works, okay? Algorithmically, it's pretty straightforward to do this, all right? We start off at any point in time, we have a set of particles at the last time step, and each particle has a state, like its position, and a weight. And we're also going to be given a new action, like take a step to the right 2 meters, and we're going to take a new measurement. And then here's how the particle filter runs. We start off with a new set of particles empty and a normalization constant of 0. Makes sense. And then we just do the following n times, where n is the number of particles that we need, all right? So the first thing we do is we sample a particle from the previous distribution, that's from this distribution here, according to its weight. Okay, so we just sample a particle, okay? The next thing we do, this is actually a combined step, okay? It says control, but it really should say control and diffusion, right? We sample a new state using two things. Whatever the old one was, so that's the value we pulled from the particle, right? That's this xt here. We've sampled a particle. It has a particular state. That goes right in there. We also have the action. And then we have to sample from the new distribution. So let's suppose the action is take a step a meter to the right. Every time I do this, make it go, all right, take a step a meter to the right, and then I'm going to sample from a distribution because there's actually some uncertainty about that step, right? That's our process noise. So it's a little tight Gaussian. I generate a little bit of noise, and I add that. That's what this sampling value is here, using the previous sample, the control, and then whatever the noise is, okay? Then what I do is I re-weight that sample. What do I weight it by? I weight it by how likely would the measurement have been, this is my likelihood, okay? How likely would that measurement have been if that new sample is actually where the object was, or where the robot was? That becomes my new weight, all right? That's the multiplication step we did before. We took our prior, we had those lumps, we multiplied them, and we got them through. We just keep track of the sum of those weights. We add that particle to our growing set of particles, and we do this n times. Now we're all done, except one problem. Our weights don't sum to what? They don't sum to 1 because they were whatever they were. We just did this multiplication. So all we have to do is, because we've been keeping track of the sum of the weights, that's the eta, we divide all the weights by that value. That's normalizing the weights. When we're done, we have a new distribution, bunch of particles. Each particle is at a particular state. Each particle has a weight, and the sum of those weights is 1. And so that's a valid sampling-based representation of the probabilistic density. And that's it. That's all of particle filtering. Just stepping through this diagram, okay, we start off with some underlying distribution, pardon my inability to trace, okay, but of course we don't actually have a real distribution. What we have is a set of particles, Okay? Those particles are not uniformly weighted. Remember, the sum of all the weights is 1. Some particles have more weight than others. That is, that particle has a higher probability. All right? So here's what we do. The first thing we do is we draw a set of samples from this set. Okay? Now you'll notice here in this nice picture, one of my big particles happened to get sampled 3 times. The medium particles got sampled twice, and this one got sampled once. And by the way, notice, how many times did these itty-bitty particles get sampled? Not at all. That's okay, because you're doing a random sample because it corresponds to the density. And that random sampling sometimes gets all the particles, sometimes only gets the ones with significant weights. So we do the sampling. Now the next thing you'll see is that each one of these particles has been shifted, but you'll notice that the shifts are not always the same. So why do you think that is? Do you know why that is? There's a deterministic part. Nothing says that my deterministic part has to be the same for all my guesses of the previous state. Okay? Let's suppose what I do is I take a step proportional to the number of lines that are on the floor, right? So I'm going to step 3 lines. But if the lines are closer here than they were over here, relax, Megan, then going 3 lines over here would actually mean I'd moved a smaller amount than if I was over here. If I had gone 3 lines, I would have gone a further amount. All this means is that the deterministic part doesn't have to be the same everywhere. It's just deterministic. Then we add in essentially what could be thought of as the diffusion part or the uncertainty part. Remember when we were generating the new sample, we did the deterministic part plus the probabilistic part. And that's what's here, right? So after we take a sample and we move it, we add some noise, and we do that every time we had drawn a sample. So since we drew 3 samples from this particle, it ended up at 3 different places. Likewise for all the others. Then what we do is we take our measurement, and we've got P of z given x. That's what this value is. And we just multiply these weights, which are all 1 to start with, by that value. Okay? Oh, here it is, P of z given x. We just multiply it, and we end up with this new set of particles. Okay? So if I erase my figures there, you take a look. That's a beautiful figure. It's all of particle filtering. Just sleep with it under your pillow, and you'll be in great shape. So that's all there is to the algorithm that's particle filtering using sampling as a way of representing your densities. There are some details to mention about how to do that, which we'll talk about later when we do it for tracking. But before we do that, I want to show you some interesting sort of robot vision applications because they illustrate the use of particle filters really well. And then we'll revisit the pure vision tracking. But in the meantime, I'm thirsty. I'm going to go get a drink. So we'll be back for the next lesson in a bit. All right, welcome everybody. Hope you're having a great day. Back to computer vision, and we're continuing with our work in particle filters. Last time we introduced particle filtering, and we talked about the algorithm that actually implemented it. So we're using a set of particles to represent a density, and we went through the Bayes loop of essentially propagating the belief forward through both the deterministic and the non-deterministic part. Then we get a measurement, which gives us a likelihood. We multiply the prediction by that likelihood, and that gives us something using Bayes' rule that we can normalize to have a new belief, a new posterior estimate of the state. So in this lesson, we're going to look at some robot vision examples that sort of illustrate nicely sort of the simplicity of using this method. Let's take a very simple robot sensing problem, right? So let's assume that a robot knows the 3D map of its world. Okay? And for now, we're just going to worry about a robot running around on the floor, so it's not climbing stairs, etc. It's just running around. And let's assume also that it has noisy depth sensors, so it can measure depth in a lot of different directions. And they're noisy, so the measurement is uncertain, but we know about the uncertainty. That is, we have a sensor model. Okay? And it moves between frames, and it takes a set of readings, and then it moves again and takes a set of readings, and it moves again. But the idea is it keeps taking all these readings, and the question is, how well can it know its state? So what is its state? Montana? No. Its state is 3 values, x, y, and theta, its orientation. Okay, that's why we're just doing a mobile robot on the ground, 3 dimensions. All right. So just to remind you, in a Bayesian filter framework, we need four things. We need some sort of a prior. Remember that trip to Delphi, so you unpack your next prior. We need a dynamical system model, and that's the likelihood of landing in some new place given that you were in an old place, plus whatever action was taken. We need a sensor model. Remember, a likelihood. That's not the probability of being someplace given a measurement. The likelihood is the probability of getting the measurement given what your state was. And then we need this stream of observations and the action data, the Z's and the U's. For that robot that I described, the state is obvious, the map will be easy, etc. The thing that's tricky, not tricky, the thing we have to define is the sensor model. So here's a picture of a sensor model. And what this is this is the probability of getting a particular measurement if, let's say, the actual state was here on this black line, okay? And what was nice is when you're using a real robot, you can actually measure the likelihood. So you stick the sensor, 3 meters away, or let's see, that's centimeters, so 2.3 centimeters away from the wall. You turn it on, you collect a whole bunch of measurements, and you see what you get. That distribution would be this distribution, okay? And in fact, the blue is what was measured, right? So that's why the blue has got the noisy stuff. And the red is how they approximated it. And you can see they basically had some sort of a Gaussian function or something like that. In fact, you can see that the laser has a less noise than the sonar. Okay, so this is actually a relatively noisy laser. A modern laser would be, very precise, except that you might have some specular problems, etc. So all of that would be fine, except you'll notice there's this thing here and this thing there. And the question is, what's going on when, the thing is 2.3 meters away, and here it says 500, but the astute observer will notice you're just using the very last value. Well, what that really is that's the probability that you get no return, okay? So you're some distance from the wall, you send out your sonar chirp, or you send out your laser, and it just goes away, gets on a train, never comes back. This happens, you guys know what specular reflections are, right? So when light bounces off, etc. Turns out that sheetrock is very specular to sonar. So when you send out a sonar chirp, often it doesn't come back, it skips like it reflects off, in which case you don't ever hear the chirp come back, or it comes back after having gone through a long echo path. Likewise, if you're looking at something that's shiny, like a glass wall, when you point at it, you can see the laser beam, but when you point it on the side, okay, it'll be reflective, it'll be a specular. So what these values are is the probability of getting no return given that you're at some distance. And in fact, that probability stays the same pretty much no matter what your distance is. All right? So remember, this is not the probability that your distance is actually 500. It's the probability that you would get this no return at any given point in time. Okay? So we need to incorporate that noisy model. Here we have an example, and what the robot is actually going to do is it's going to follow this purple line. Okay? So this is where it starts, and then it goes here and it moves that way. What we're showing you to begin with is a couple things. First of all, you see all those red dots? That's its current set of particles. In other words, it has no idea where it actually is. The green is an example of where it thinks it might be. And in fact, this is the locally most likely, which is just some way of the robot guessing where it is. Now, what I'm not showing on this map is for each particle, there's also a theta, right? Particles have to represent the state. What do we say our state was? We said it was x, y, and theta. It's hard to show this in 3, so I'm only showing x and y, all right? But for any given theta that I think it is, then I would be sending out an array of sensor measurements, and I think I know where it should hit because why? Because I have a complete map, okay? So what happens is, first, your eye is just going to naturally go to the green thing. What's going on there is that's the set of sensor measurements that it's getting. So wherever it thinks it is, it puts down the measurements it actually got. Now, if it's in the right place, those measurements will actually, most of the time, hit the wall at the right distance. Every now and then it'll go right through the wall because it was a no return. All right? So let me just put it in motion. It's easier to understand. All right, so here we go. So it's a movie. So each one of these changes is when it takes a measurement. And you'll notice there's a clump of particles here. In fact, that's the most likely clump. And there's also a clump of particles there. That's a nice way of saying the robot does not know whether it's definitely here or definitely there. And the reason for that is the hallway is kind of symmetric, right? There are these doors, okay? But there's doors on both sides. So it hasn't yet been able to disambiguate if this is the center of my universe, whether it's at this area or that area. But let me put it back in motion. What's going to happen is the robot's going to go inside in the room, and you'll notice in this room, in the room it's about to go into, there's a ottoman or whatever that is in the middle that's not in the other room. So once it goes in, yep, there it goes, okay, you'll notice the particles that are in the wrong place, they're going to disappear. Okay. Now, some of the rays are still going in the wrong direction because, they're going through the walls, but that's just the no return. And you'll notice by the time we get to the end of the run, you'll notice that it has localized itself very well. Some of the measurements still go through the walls because I'm assuming those were no returns. But just by taking these simple one-dimensional measurements, several of them at a time, and knowing the map and taking its movements, it's able to localize exactly where it is. And that's sort of a hallmark of particle filtering. You start off with a big unknown set, and eventually a whole bunch of particles go away because they are just totally inconsistent with the measurements you get. So when they get multiplied by p of z given x, the likelihood of that measurement is so small that it diminishes that particle's weight a lot, and the next time you sample, and we said this at the end, remember very low weight particles sometimes don't get sampled at all? So what happens is only the samples that are near the parts of the sensor measurements that are consistent survive, and you keep iterating. Also, remember we had the two lumps for a while there because I wasn't sure whether it was this one or that one because it didn't have enough information to know yet. It wasn't until it went inside that room that it had that information. And this is sort of the inherent advantage of particle filtering over, say, a Kalman filter that has a single hypothesis. For those of you who've maybe heard of multi-hypothesis tracking where you end up having multiple hypotheses, one way of thinking of particle filters is it gives me just a uniform and easy way of doing multi-hypothesis tracking. Meanwhile, at the Smithsonian Museum of American History, which is just a bigger map, bigger thing, we're going to do the same thing. One thing I'll show you here is that here the map is a little bit bigger. And in fact, if you take a look at this map, it was actually created by a robot doing what's called SLAM, where we actually used the robot to build the map. So here we have, again, the robot doesn't know where it is. It takes a bunch of measurements. These are where the actual measurements are. The robot doesn't know that yet. And this is the set of particles that survive. So you see it's clumped up a little, but it doesn't know. So it moves, takes another set of measurements, and these are the particles that survive. Now, with just two sets of measurements, almost everything else here has gone away, and we're getting a bigger clump there. Just two sets of those measurements, right? Propagate forward, take a measurement. And now you can see as it's advanced forward, it has pretty much very little ambiguity left. So again, just by taking these simple measurements, it knows where it is. How about some very simple vision? Real honest, so we're not using a depth sensor anymore. And this is about as simple a vision as you can imagine. So this is work that was done by Frank Dellart, who's a professor now at Georgia Tech in our robotics and vision group. But in 1997, he was like 6 years old, it looks like. No, that's not Frank. That's some kid at the museum. Frank was doing his PhD at the time. He did something very cool. They said, you know, we've got this ceiling, and the ceiling has lights in it. If we had a map of the lights, we should eventually be able to figure out where we are by just, do we see light or don't we see light? And the way that works is you had a robot with a little camera that just looked up. All right, here's that little square. And it would just see, did I see something bright, medium, or sort of dark, right? It could just get a small number of sensor values. Or you could think of it as just taking the total value as saying, about how bright is that spot? Now, to do that, what I have to be able to do is, given being anywhere in here, I have to know what is the probability of getting that brightness in the image. So that's what this shows here, that if this was actually the brightness, this is the probability of the brightness that I would see. So the idea being if this is the actual brightness of the state X, of the position, then this is the likelihood of what I would see. So for example, suppose I'm under a light, okay? So typically what I see is this brightish patch here, and this map is the likelihood of getting that bright measurement at these locations. And by the way, in this map, the black are the high points. So you see each one of these lights. So if I was actually under the lights, the likelihood of seeing something bright is high. Otherwise, the likelihood of seeing something bright is low. Sort of near a light, I'm going to tend to see these gray things. And when I'm far away from a light, I'm going to see mostly darkness. So those are our P of z's given X. And then here's the thing running. And it's a little hard to see. You see all these red dots going. And what's happening is the robot is actually following this red line. And it comes in and it goes down. And you'll notice after a little while, it knows exactly where it is. Now it's going to turn off to the right over here somewhere. And if it hangs out in a dark area for a while, its uncertainty grows because it doesn't know exactly where it's moving in that dark area. Okay? So you're watching it and it's doing some cool stuff. What's interesting is, so we have this map of the thing. We can compare two things. The robot knows the commands that it gave to its wheels. Okay? So it knows how far it thinks it went. It also knows how much it thinks it turned. You guys have an odometer in your car? Odometer measures distance. Odometry is when you measure how you think you moved based upon how your wheels turned. If we plot on this map where the robot thinks it went based upon its wheels turning, we see something that looks like this. Okay? And the reason we know that that's wrong is that these are areas that it can't actually go through. And you see it gets sort of right, but then it sort of gets a little confused, and it's going through parts that it can't actually go through. When we add vision, and why do I say add vision? Well, we still use the odometry as the deterministic part. Megan jumped for that thing, right? So the odometry says, well, you moved a foot to the right. Okay? So we add that. That's our prediction part. So we still use the odometry, but then the measurement from the vision improves our result. Okay? And that gets us the much better result. And this is using essentially a camera just looking at a little area and saying, am I bright or am I dark? Or how bright is it? And I have a map of the ceiling. So it's pretty cool. Well done, Frank.
So you still don't believe all this particle filter mumbo-jumbo. Let's try a simple example. Here's an ant scurrying along on top of this crossword puzzle. It's one of those computer sciencey ants, so it only moves one step at a time, either horizontally or vertically. It can sense whether it's on a black square or white square, but that is it. It has no other way of knowing where on the puzzle it is. Here is a sequence of steps that the ant took. The first column is time t. The second column is its observation z, which is 1 for white and 0 for black. The final column is the action taken, or u, which is basically what direction did the ant move in. For instance, at t equals 0, the ant saw that it was on a white square, and then it moved up. At t equals 1, it observed a black square. This was the result of moving up in the previous step. Okay, the next action was moving left, and so on. Can you figure out where the ant is at t equals 5? Mark the appropriate checkbox, or boxes if you're still unsure. Okay, let's see how a very simplified particle filter can help us estimate the ant's position. Initially, at t equals 0, we have no idea where the ant is. So we might as well assume that it is in one of these squares, any one of them. This is our initial prediction. Now the observation says that we are on a white square. The likelihood of us getting a white observation when we are on a black square is really low. So in our simple case, we get rid of the particles in the black squares. You can think of this as a correction. Okay, now we see that the action taken was move up. So we take our entire distribution of particles and we shift the whole thing up, like that. Any particles that went outside the valid area are discarded. Now this is our best guess or prediction at time t equals 1. This time we see that the observation is black. So all the particles on white squares are basically inconsistent with the observation. As before, we get rid of them. Alright, our next step at t equals 1 is to move left. Observation at time 2 is white. So we get rid of all the black particles. Next, we move up. Interestingly, all the particles on the board are consistent with the observation. At step 3, we move up again. Now the observation at step 4 is black. So we get rid of the white particles. Now we're left with only 3. Well, from here we move right. And the observation is white, so we get rid of the one black particle. And that's it. We're left with 2 possible positions for the ant. Since we don't have any further information, that is our best guess. Are you wondering where the ant started? Well, it could have started here at t equals 0. Move up, see black, move to the left, see white, move up again, white, move up, black, move to the right, and you see white. But that's one possible path. The other starting point could have been down at the bottom here. Same thing, move up, black, left, white, up, black, right, white. So, particle filters, useful, aren't they?
Before ending this lesson, I want to talk about a couple of practical considerations of particle filters. And the first one involves sampling. As you can imagine, sampling is really important, okay? Because I have this set of samples, and every step I have to generate a new set of samples. So I have to resample it. I go grab a sample where the probability of pulling out that sample for state X is proportional to the weight of that sample. And typically, I'm doing this a constant amount of time, so n times. So I'm using 1,000 samples, 10,000, however many samples, I'm doing that every time. We'll talk, actually not today, but next time, that number can get kind of big if your state space gets large. So being able to sample effectively or efficiently or less often is kind of important. So I want to talk about resampling a little bit. What we have here is an outer ring, okay, where the idea is that the arc length of that ring is proportional to the weight. Okay, so, you know, W1 is small, W2 is bigger, W3 is huge, et cetera, whatever. And these are all the weights, right? So you can think of sampling as following. I just randomly pick a direction, and if I hit W3, I'm going to take sample number 3. So that'd be my first sample. All right, do it again. If I hit WN, I pull out the nth sample. And basically, I have to keep doing that n times, right? So it's like a roulette wheel. I spin the roulette wheel n times, and I have to figure out where I land. And that figuring out is actually a binary search, so that's log n, but I do that n times. So it's an n log n operation. So that's kind of, it's not awful, but it doesn't scale linearly with the number of samples you use. It goes up by n log n. It turns out there's a cute little trick that you can use that is, instead of like a roulette wheel, is more like a wagon wheel. And the way it works is this. So let's suppose I have n samples. I can make a set of spokes that are 1 over n full rotation around. So here I've got 1, 2, 3, 4, 5, 6, 7, 8, right? So each one is 1/8 of an arc. And what I can do is I can randomly put it down someplace, and if I've randomly done it, then I can just read off for each one of these spokes which W did it hit, okay? And in fact, the starting weight, right, I can just start at some random one here, and I see what W am I at, and I go to the next one, and I see, did I pass a boundary? If so, then I'm at the next W, and likewise. So what's nice about that is that's done in constant n time. And it's sometimes called stochastic universal sampling, systematic resampling. The nice thing about it is that it's a linear time complexity. You know, if you do 10,000 points, it takes you so long. If you do 20,000 points, it takes you just twice as long. All right? And it's very easy to implement. In fact, it's so easy to implement, let me show it to you. So here I'm showing you that actual wagon wheel algorithm that we just talked about, this systematic resampling. You start off with no new samples, and you build the C's are going to represent the outer ring, the cumulative distribution function. And essentially, each one represents the one before it plus the extra new weight. right? So you start off at the first weight, and then C2 is the sum of W1, W2. C3 is sum of W1, W2, W3. That's that outer ring, okay? You can think of it that if it goes from 0 to 1, because everything sums to 1, then the C's are sort of how far, what percentage around the clock have you gone. The next thing you do is you have to pick, remember I told you you have to sort of randomly throw down the wagon wheel to start with? Well, if the wagon wheel has 8 spokes, the first spoke has to go somewhere between 0 and 1/8. That's what this is right here, right? N to the minus 1, maybe to write as 1 over n. That's the offset. And then what you do is you go around the outer ring saying, wait, did I pass my offset yet? As soon as I've passed it, that's the CDF part that I'm in. So just drawing that on here, if this is my first one, right, and this is where it starts on the outer ring, I say, did I pass it yet? I say, nope. Okay, did I pass it yet? Yes, I did. So this first spoke landed in W2. Then I just go to the next spoke, and I say, did my last marker pass it? No, I got to go to the next one. Did this pass it? Yes. So my next one is from W3. So that's all I do is I initialize it, and then I just count up for however many samples that I need. I go and I grab the next wagon wheel chunk, and I see where on the CDF that it lands. And then I just return that set. It looks more complicated than it is, and it's a way of doing that sampling in linear time. That's sort of how to do sampling efficiently. The other thing is, how often do you have to resample? Well, in the algorithm that I showed you, we resample all the time, and that's so that we have a whole bunch of samples that are about uniform weight and we spread them out. If I don't have too many samples that have very large weights, maybe I don't have to resample. Maybe I can just reuse the weights, the same samples over again. Right? I still have to apply the deterministic part, and I have to apply the expansion part, but I don't have to do that resampling. And you can do that by just saying, let me take a look at sort of the variation in the weights. I want them as uniform as possible, and as long as they have a certain amount of uniformity to them, I won't resample. So that reduces the number of times you do resampling. A second problem is, what if P of z given x, what if your likelihood is incredibly peaked? Remember, you multiply the likelihood times the weights of the samples. If it's incredibly peaked, that means that P of z given x is 0 almost everywhere else. That's not very helpful, because what that means is you've wiped out all of your possible predictions. In general, you want to allow for noise in your P of z given x. Don't be so systematic about it. And you also might want to be better at sort of how you do your proposals to begin with, right? So you want to make sure that your particle filter sort of spreads out the points to begin with. And one way of doing that actually is, if you think of a sample, each sample you can think of as having its own little mini Kalman filter. So you can think of it as having a Gaussian that sort of spreads itself out and goes forward. In general, you're much better off overestimating noise and let your measurements sort of narrow you down than underestimating noise and have your measurements think that they're much more accurate than they are, or I should say much more constraining than they are. Another issue is recovery from failure. Suppose an object really did disappear and reappear. If I have no particles there, I don't have any way of tracking it ever. So a standard thing to do is, each iteration, you randomly put out some particles everywhere, or sort of uniformly distributed. Because if my measurements suddenly have moved over here, there'll be some particles over there, and eventually that will be the distribution that will be tracked. So those three issues of sort of making sure you're smart and efficient about your resampling, not letting your system think that measurements are too precise, and making sure you have enough noise so that you don't kill off samples too quickly. And this idea of having some random samples distributed in a useful way so you can track things if things change very unexpectedly. All these things are necessary to make particle filtering work. That ends the robot vision part of particle filtering. Now, if you remember, we introduced all of this stuff in order to be able to do tracking. Okay, we started with Kalman filter tracking, then we did particle filter. So in our next lesson, what we're going to do is we're going to go back to doing tracking, and we'll use some simple particle filter technique for doing some visual tracking. All right, welcome back to computer vision. Today what we're going to do is we're going to finish up particle filtering, and we're going to sort of do particle filtering for real. We've mostly discussed it from an algorithmic perspective and sort of how it maintains a density estimate. And we even looked at some robot vision examples last time, localization through the Smithsonian and other things. And this time we'll talk a little bit about real vision and how you might do it. So if you remember this Bayesian filter framework, we had to have sort of 4 different elements, right? We needed a prior, which nobody ever talks about. It's kind of the black sheep of the family. A dynamical model or an action model that says how we think things change from moment to moment based upon where they were and the inputs that are provided. A sensor model, the likelihood of a measurement given state. And then we have this stream of observations, and the question is what to do with them. To do real tracking, we have to specify these things. In particular, we've got state and state dynamics, and we've got a sensor model. So in the math, it's easy. We just write X, and we say X is the state. But the state of what? Montana, with Missouri, you know what? No, it's state of the object. Everybody says, oh, it's the state of the object. Well, what does that mean? Obviously, some representation of the object, its position, its velocity, maybe something about whether it's happy or sad. And that sounds like a joke, but actually, if you can think about tracking the state of the object, there's no requirement that the state be a purely physical thing. It's anything that can have an influence on a sensor measurement that you want to know. Speaking of sensor measurements, or speaking of Z, that's the measurement. But the measurement of what? What measurement are you going to use, and how does the measurement relate to the state? So if we're going to do real tracking, we have to know these things. And finally, where do you get your dynamics from? Do you go to the dynamics shelf at Home Depot and say, I need some dynamics, please? Where are you going to get these for computer vision? The discussion we're going to use today comes a bit from this paper, and the idea of using particles and sample-based representations of densities, that wasn't new. That was known in a variety of mathematics and other engineering fields. But this is the paper that really brought it to computer vision. We showed this picture already, right? This is a picture of the tracking of Andrew Blake's daughter. And the first question is, what is this state? All right? And the state, or the object that was to be tracked, was a hand-initialized contour of the head. On the left here, you see a bunch of contours, okay? In fact, there's even one that's up here, all right? Those contours are the contours represented by each or many of the particles, the top particles, right? And so, for example, you can actually talk about the mean state as being the sort of average of the particles. But that doesn't really tell you what it is. What do you mean, the state of a contour? Well, in fact, what they did is they drew a contour and they said, because that's not a parameter, that's a shape, and they said, let's represent the state of that contour by an affine deformation, okay? Remember affine? Affine is, it's a 3-point to 3-point mapping, takes how many parameters? It's 6 parameters, okay? Translation, rotation, scale, and shear, depending upon how you count those. I mean, it's 6, and you can sort of divide them up any way. So the idea is that each particle represents a 6-dimensional vector. So by the way, that means our particles are living in a 6-dimensional space. And the bigger the number of dimensions, the more particles you need to sort of fill up that space. In fact, it doesn't grow so nicely, does it, right? I mean, if I go from 2 dimensions to 3 dimensions, right, if I had 100 particles before, if I wanted to have the same density, I would now need 1,000 particles, right? It grows exponentially in terms of the number of dimensions. So for affine, we're going to need 6. And as I said, each of the particles represents that. Here, by the way, is one of the videos, and one of the questions you might ask is, well, where do you get the dynamics?
Where do you get the dynamics?
Well, there are a couple of things you can do. The easiest thing to do is to cheat, all right? So the reason we're using dynamics here is that the girl is jumping up and down in front of a cluttered background. So to keep track of where her head is kind of a difficult tracking problem. That's why we're doing all this work to begin with. That's why we're using particles. But when would tracking be easy? How about if she was jumping around in front of a green screen or a white background, okay? Or in fact, even easier, suppose you put her in a totally black turtleneck sweater and you put her in front of a black screen, kind of like that thing. By the way, Megan doesn't let me wear black shirts because I'll disappear. But the point of my disappearing is all you would see would be my floating head, which would be kind of creepy. But it would be very easy tracking. So you could have somebody jump around with their floating head, track it very easily, and measure the dynamics. So one way of getting dynamics is to sort of cheat and get it from an easier system. And I think for a bunch of the stuff they did in condensation, that's what they did. They had an easier problem. Something else they did was they tracked the state of the hand. So what do you mean the state of the hand? That's actually, I encourage you to read the paper. They did a couple of really cool things. First of all, you have translation. Okay, well, how many degrees of freedom in translation? Well, we're doing it in 2 dimensions, so there's 2 degrees of freedom. They had a rotation, okay, which is 1 degree of freedom. But the other thing they added to that was the shape of the hand. And you might ask, well, how did they encode the shape of the hand? Don't bother, Megan. Well, actually, what they did was they took a whole bunch of images of contours, and then they did a form of principal components analysis. Now, you may not know what that is, but the good news is you will. Very soon, we're going to do principal component analysis when we talk about recognition. The thing that matters is that it has a low-dimensional representation of a certain variation. And what they did is they extracted out, essentially, instead of keeping rotation separately, they took 10 degrees of freedom that represented the shape of the hand, including rotation. So you had 2 for translation and 10 for the rotation and shape. So that's a 12 degree of freedom space. So that's even more difficult to do the tracking with particles, because you have to have a lot of particles in order to do this. Okay, that's about the state. What about the measurement? Okay, what about Z? All right, here's another picture taken from that paper. And what they did was, in fact, if I go back to the hand thing, you'll see that the hand, what they want to do is track this contour. All right, and I'll draw it on the hand part. Well, if you've got the right state, then you would expect to have an edge in the image at the edge of where the state says the fingers are. That is, there's some relationship between the edges of the fingers in your state and the edges that you would see in your picture. And in fact, that's what they do. Okay, what they do is, and there's more derivation, basically they come up with a probability distribution that says that the probability of getting a particular measurement given the state, and remember the state tells me where the fingers are, is essentially an exponential, so like a Gaussian, that's proportional to the square of the distance to the nearest strong edge. So that was the original condensation paper. Like I said, it was in '98. There have been many versions subsequent, things that have to do with importance sampling that look at the particles and stuff. Here's another example of doing head tracking, 2002. And you can see it's a little hard right there, tracking the head there. Okay. There's an interesting example right here. You see the head here is fully visible, but then it goes behind the cabinet. In fact, the only part of the head that's visible I just outlined. In fact, only the top half is visible there. So the question is, how did they move through occlusion? Okay, because part of the head is missing. Well, maybe they used velocity in their state, or maybe they didn't. What do you think? You think they did, or you think they didn't? Personally, I would have thought they did, because, I mean, I know all about Kalman filtering. I know if you track velocity, it's really easy. But then, if I think about particle filters, I'd say I probably didn't need to track velocity for the following reason. It's not the case that it has to be a great example of a head contour. It has to be the case that the example of the head contour that's here is a better example than if I put the head somewhere else. And in fact, indeed, this paper, they tracked the head through the partial occlusion without velocity. Now, would it have worked if the head was totally occluded behind the cabinet? No, because then the thing would just stay there. In fact, they call it a velocity zero model. The particles just stay where they are and they just diffuse out from the uncertainty. And so if you showed up on the other side of the cabinet, you'd be out of the frame of view altogether. Yes, Megan, I'm back. Okay. Whereas if you did velocity, you would follow me. Follow me. There you go. Follow. Very, very good. So now you get the point. You can do interesting things with states. So here we have the head contour. Another kind of model is, suppose you've got some way of detecting colored blobs that represent, say, hands and head. Now your state might be the XY location of the hands and head, and your measurement might be where you think the colored blobs are, and your sensor model might be how well the predicted blobs match the color. You can use sort of any model you want as long as you can have a state and you can talk about how that state expresses itself. In fact, here's an even better model. Suppose you want to track some region of a distribution of colors, right? So like maybe this region here, or this region here where you can see the ellipse, so that kind of gives away that the region that we're gonna be tracking here. What would be a good model or state for tracking that, okay? Well, clearly you want the location, because after all, I want to know where the thing is, all right? And if I've defined a region, I want to know sort of how that region is changing, maybe a little bit in orientation or size. But just to tell me the position and size, that's not enough. I need something about the appearance. In this particular method, and we're going to talk a lot more about this next time, what they tracked is really cool. They tracked the distribution of colors. Right? So if I look over, let's say, I won't do that region, I'm going to do this region over here, right? There's some white pixels, there are some reddish pixels, there are some brownish pixels, and as that player moves, the shape will change into form, etc. But the overall distribution of colors might be quite similar, right? And in fact, what you have to say is, well, what's a reasonable sensor model? And we're going to get to that next time. But basically what you're going to do is you're going to compute the similarity of the color distribution of what you had and the color distribution of your proposed state, all right? And you'll need some way of comparing those color distributions. And just as a way of showing you how well this thing works, here's two examples. This is actually done using mean shift filtering, but could also have been done using particle filtering. And we'll talk about that both next time. How about a really, really simple model? Would you like a really simple model? Well, of course you would, because who wants a complicated model if you can have a simple model, all right? Suppose we just start off with a patch, a location at some point XY, all right? So we're going to say, all right, I've got some patch at XY. And my dynamics is going to be random noise. So what that means is that's the same model that they use for the head contour. We're not going to track velocity. We're just going to assume that the position changes randomly. Okay? So as you add your particles, you assume zero velocity, so they stay where they are, and then you would add random noise. And then how about the very simplest of sensor models, okay? You just take the mean square difference, right? So what this says is if I propose that the state of the object is here, and it used to be here, I'm just going to compare the patch. I'm literally going to subtract the two patches and say what's the mean squared error, okay? That would be sort of the simplest sensor model possible. You could do a slightly more sophisticated one, right? You could do a normalized correlation. You've already learned about this when we did stereo, and you could say the higher the correlation, the more likely, or the bigger the sum of the square differences, the less likely. That would be your sensor model. So to do this, all you would need is a patch. So there's a patch. So those of you who are from the United States or know U.S. politics, that's Mitt Romney. The reason I'm showing you this is that we provided to the students who are going to be doing problem sets in the original class and going on the OMS class a video. Okay, and this is the patch grabbed out of a section of one of the frames, and your goal is to see with a particle filter how long can you track Mitt Romney until until it falls off and he loses the election. That ends this section specifically on particle filtering. You've now seen the algorithm and some details about state and dynamics and sensor models, and the really good thing about particle filters is that you can make them as complicated as you want, but you can start off simple and get something running. You then have to worry about how many dimensions are in your state space, because if you get too many, then you might have to have too many particles. You have to worry about reinitializing. We talked about that before, of scattering some particles around in order to in case something has happened quickly that you didn't anticipate, that there'll be some particles there. But the good news is that it's really quite accessible. There are a lot of papers to read. You can actually start with that condensation paper. It really lays it out. In fact, there's a conference version of it that came out even earlier that I think is even clearer because it has less detail. So I hope most of you will get to understand that, and certainly the OMS students you will, as you'll be doing it on the problem set. Welcome back to Computer Vision. Today, finally, we get to finish up on tracking. We've discussed tracking a few ways from the Bayesian inference perspective, where we have a dynamics model, and you know the whole bit now at this point, where we predict forward the state, we take a measurement, we do our correction. One was a Kalman filter, where essentially we have a specific representation for our densities, namely Gaussians, and all the world's a Gaussian. Then we discussed particle filters, where because we're using samples, you can have much more arbitrary densities. You just have to have enough particles to represent them. And also you need a generalized sensor model, which works well. For this last section, just talk about a couple more methods, just so you should see that they're being done. And then at the end, I'm going to talk about some issues that show up in tracking, no matter how you're doing it. And it's sort of outside of the main tracking conversation, and yet if you don't deal with those issues, nothing works. Mean shift is a method that's easiest to introduce when we do segmentation. The idea is, in mean shift, is to find the modes of a distribution or of a probability density. So remember, the modes are sort of the peaked areas. And here's the basic underlying assumption. The assumption is I've got a bunch of samples that have been drawn from some probability distribution function, and you want to find the modes. So there's this beautiful, couple of beautiful examples out there on the web. Feel free to steal whichever one you want. I stole this one. So here we have a set of particles, and they're just drawn from some density. And probably if I were to ask you where is the mode, you'd probably say that it's somewhere around here. Okay, and the goal is for the system to find that on its own. So here we have, again, we have our sample. So let's put down a region, okay? It's called a region of interest. Now, we're not going to talk about the size of that region just yet, or its shape. We'll talk about that a little bit later. It's going to be a Gaussian. But for now, it's just going to be a circle. So we have this region, and we calculate, okay, of all of the points in that circle, where is the mean, or the center of mass? And we say, oh, it's not right in the middle, and that difference between them, that's called the mean shift vector. So this is called the mean shift algorithm. Amazing, huh? And so what do you do with the mean shift vector? Well, you shift the mean. And there it goes. Da-da-da-da-da. Perfect. Okay? What do? We do it again. Okay? Here's where we are. Here's the weighted mean of the new samples. There's our mean shift vector. What do? We shift it again. Ta-da! And we do it one more time. There it is. Oh, we're getting close now. Small mean shift vector, shift, and then finally, guess what? We are in the right spot. What's kind of cool about mean shift, a bunch of things, is under some reasonable assumptions, like the shape of the thing that you put down, which is a kernel kind of thing, you can prove that in most circumstances, this thing will converge. So it'll actually find those modes. And that's really cool. So what does this have to do with tracking, you might ask?
What does this have to do with tracking?
So basically, mean shift tracking is, instead of just tracking the mean of a distribution, we're going to try to track essentially something about a distribution of a region. I'll make that clear. But our methodology is pretty similar to before. We have some position that we start with, right? And here, by the way, our initial model is not just the location, but it's this region and the size of that region. And what we have to do is we're going to search in a neighborhood in the next frame for that same description, okay? And when we do the search, we're going to move around in X, Y. We might also do things like change the scale, all right? And what we want to do is we want to find the new location, maybe scale, maybe some other change, maybe an orientation thing, that maximizes some similarity function, all right? And then we just iterate. We connect the dots. And we repeat the process, and we get this beautiful animation that says, okay, the new maximum becomes the start for the next frame. The thing that makes this mean shift tracking is essentially what the model is and how we compare them. So we've got this initial area that we want to track, and we have to choose what the model is going to be. And in mean shift, what we do is we choose a feature space that is the quantized color space. So what that means is that we carve up the different RGB values into a histogram. So it's written as a 1D histogram here, but it's typically a three-dimensional histogram, R, G, and B. You might carve R up into 4 bins, G up into 4 bins, B up into, say, 4 bins. That'd be how many bins together? 4 times 4 times 4, 64. Okay, in which case you'd have a 64-bin histogram, and every point within that region, you take its color and you'd put it in the right bin, and that would give you your probability histogram, which you can think of as a PDF, of the color over that region. That's the representation of the region that we're going to try to track. Okay, so here we have two frames. On the left, we have the original model. The model is sort of a time, and we're going to call that 0. And on the right, we have some candidates, someplace in terms of how it's changed. And this can be centered at some value y, some pixel y. So on the left, we have our initial distribution. Okay, so this was our histogram that we computed in our area, and it's typically called Q. And Q has got a set of bins, U, 1 through M. And because it's going to represent a density, we enforce the fact that the sum of them equals 1. So how do we do that? Well, we just sum them all up and we divide all the bins by that value. Okay, and you see we have the audaciousness to call it probability, okay, because, well, we're going to take these samples and we're assume that it's representative of a probability distribution function. So that's our distribution at the initial of the target. At some new location, okay, we can compute the distribution again. So now P of u is a function of y, where y is the point that we're considering. Remember, you have to consider P of z given the state. So y is going to be that new point. And it's called y instead of x. That's how it's done in the mean shift literature. If you read this, this is what you would see. And again, we're going to build a distribution by assuming that these things sum up to 1. So we have these two distributions, and what we have to do is we need a similarity function that compares them, that compares the original Q and the new P of y, which is the density at this proposed place. So the question is, how are we going to compare these distributions? Now, there are a variety of functions that you can use to compare histograms, where the histograms are normalized to 1, so they represent probabilities. There's the min value, there's chi-squared, variety of them. The one that was used with respect to mean shift tracking is referred to as the Bhattacharya coefficient. Bhattacharya coefficient comes from something related to the Bhattacharya distance. It's simply a way of comparing distributions. What you do is you take your distributions here and you change it by taking the square root of each of the components. So if Q is a distribution Q1 through Qm, then Q prime is going to be square root of Q1 through the square root of Qm. Same thing with the new proposed distribution P around y. We're going to take P prime where we take the square roots. When we define it that way, the Bhattacharya relationship is defined as follows, okay? Just take the sum over the product of those square roots, okay? And you might ask, well, why would you do that?
Why would you do that?
Well, you quickly realize that if you take the magnitude of those square-rooted vectors, right, the magnitude is the square root of the sum of the squares. Well, the sum of the squares is what? Well, since the sum of the q's is 1, the sum of the square roots then squared is going to be 1, so the magnitude is 1. So these magnitudes here, those are 1. So that means you just have this. So basically, you're computing the dot product, the cosine of the angle between the square roots of those distributions. And that sum of the square root, the thing in the box here, that's what's referred to as the Bhattacharya coefficient. It's just a way of comparing distributions, and so that's what they did. So we need one more thing to finish mean shift tracking. You remember before, when I was showing you the mean shift example, we were plopping down a circle, right? And I said, we'll worry later about the shape of that. Well, that circle can be thought of as a uniform kernel. What I mean by uniform is that its height is the same everywhere around, and it happens to have a circular shape, and it would be written like that. That's not such a great kernel. What do you think a better kernel might be? Well, instead of using the uniform kernel, we could use something that is differentiable, we'll use that in a minute, isotropic, all that means is that it's the same in every direction, monotonically decreasing kernel, and there's a certain convexity property, you're not going to worry about that. So what's our favorite differentiable, isotropic, monotonically decreasing, always positive kernel? Yes, it's the Gaussian, okay? So here it's written just as a constant proportional to a fall off by the square of the distance, okay? You can also have a scale factor, right? So if you wanted, you could talk about like the sigma, sort of the scale of the kernel. What's really cool about this is that unlike the uniform kernel, which goes straight and then falls off on the edge, this is differentiable, okay? You can know how much it's changing, and it also means that it goes down to 0 at the edges. So as you slide that kernel along, a new point, it just has a very, very small weight. In fact, an infinitesimally small weight, and then it grows. Likewise, points that are right near the top, their weight doesn't change very much, right? Because as you slide it along, the weight stays about the same. The points that are going to have the greatest value are the ones that are along the slope. What that means is you can know how your function changes as you move. That is your overall function, so your Bhattacharya coefficient, for example. And what you can do is you can use this gradient to essentially hill climb up your similarity function, right? So you can, by computing this, you don't have to sort of blindly search. You can actually follow that gradient and get to a local maximum, all right? And that was the basis of mean shift tracking. So now, going back to our previous example here of the ping pong, right? We start with the current frame. We want to search, but now our search can actually climb to the maximum of this function using that gradient information. And that's mean shift tracking. In the example shown here, remember we talked about a feature space that might be 4 by 4 by 4 for RGB? Well, they did 16 by 16 by 16. And then they manually selected a target on the first frame. So you can see here that, see this ellipse that's been put down here and this ellipse that's been put down there? They specified that in advance and they said go. And that one starts going, and I'm going to say go here, and that one starts going. And I want you to notice, whoops, let's get rid of how well those mean shift models stick to the players, okay? The average number of iterations was only 4. That is, from one frame to another, they had to do the mean shift thing 4 times to track the density. They also worried about scale in terms of looking at how the scale changed. There is, however, another way of thinking about the tracking that I just showed you. Let's not worry too much about the mean shifting part of it, and just this idea of using the color distribution as the matching of the color distribution, the similarity, as a sensor model, okay? Because when we do this mean shift and we're tracking the single peak, we're a little bit back to like our Kalman universe, right? Where the idea was there's a single hypothesis. We could just use this similarity function, the matching function of the color distributions, as the sensor model for particle filtering. That is, your particles spread out, and they want to say, well, what's the probability of getting this sensor measurement if that's actually my state? Well, you can simply say, well, it's just a measure of how close the color distribution is using that Bhattacharya distance or some other way of comparing distributions. And in fact, people have done this, and now I have to show you a totally unfair slide. And the reason it's unfair is this slide I was looking at, this is in a presentation given online talking about mean shift. I don't actually know the source of this picture, so I can't give you the reference to go look it up, etc. And then they show this interesting thing where the mean shift is tracking this cute little kid and then falls apart. Okay? Now, why would it fall apart? This is a little bit sneaky. You'll notice this brown envelope, cardboard box in the background. It has some color distributions similar to the face of the kid. So if you've ever thought little kids are really pretty much cardboard boxes, you're right. Or at least that's what mean shift says. And then what they showed is that if you used a particle filter tracker, it falls off a little bit. See, it fell off, but then it catches back on. That's what particle filters do, right? They entertain multiple hypotheses, so even if some weird hypothesis is looking good, as long as the real one eventually becomes better, it'll come back to it, and that's what it's showing here. But basically, the idea is you can use the similarity function of the two color distributions as your sensor model for a particle filter. And this relates to this idea of what I said before, that particle filters really are pretty flexible. You can pull out whatever sensor model you want to use as long as you can put it within this Bayesian framework of P of z given x. One more little a specific tracking method. And this comes from some work of tracking people, in particular their limbs and stuff, by learning their appearance. And the idea is they build a person model. And the person model is made up of a couple different things. It's made up of an appearance, we'll talk about what that is in a minute, plus structure, plus dynamics. All right? Now, the structure and dynamics are generic. That is, they are the lengths of my body, the dynamics that are how they can move, so what are the speeds people tend to move and some of the process noise. But the appearance is person specific. Okay, so the idea is I'm going to learn the appearance and then I'm going to do the tracking, and that's represented in this picture here. All right, so the idea is, given some input examples, we build the model, and the model is, like I said, it's generic structure, but we might learn the colors and the textures of these different parts, and then using that appearance and the structure, we can do the detection running on the new frames. Here's the reference, Ramanand, Forsyth, and Zisserman, and this is showing you them tracking those people parts. And the idea is that they use appearance. That's all I want to talk about, that specific method. A bit later, actually, towards the end of this course, we're going to describe some recognition methods that use a lower dimensional space for doing recognition. We've mentioned principal component analysis, etc. Once we do that, we can talk about a couple more, one or two more tracking examples that use a PCA-based description as their appearance model. But until we have that, it would be premature to talk about it. So finally, I just want to talk about a couple of issues that you'll always face when you're doing tracking. So the first one is initialization. How do you start the thing? And there's no good answer. The examples I showed you before were done manually. Somebody says, oh, track that. Okay, so you draw a little sort, say, keep track of that thing. You might have a background subtraction method. Okay, so every now and then you may be able to subtract that background, find the objects, and say, okay, keep track of that object because it's isolated, and I'm going to track it as it moves along, even when it becomes like partially occluded or with other moving things in the way. Or you might have a detector that can detect things when they're clear and fully visible, right? So I've got a bank robber detector. No, I might have a particular car detector, and I say, a Jeep has just showed up, follow that Jeep. So the detector is running, and it'll only fire sometimes when it gets a good, clear view of something, but then you want to track and follow it through. Next question is, where do you get your sensor and your dynamics models from? Well, we've talked a little bit about this. Your dynamics models, you maybe can learn by essentially from real data. That's generally pretty hard, because if you could track the real data without the dynamics model, you wouldn't be using the dynamics model. So you might use it from clean data. Remember we talked about the girl jumping in front of the black background? That would be some clean data. Or it says here you might specify domain knowledge. That means you're like the smart person. You just write down what it is. Or you take another trip to Delphi and you get another thing from an oracle. Now for the observation model, typically it says generative observation model. What that means is, remember we did the model for the robot sensing distance? So if I knew the wall was 3 meters away, and I take some measurements and I collect them and I get a distribution, now I know what my distribution would be. The trick is I had to know that the thing was actually 3 meters away or 2 meters away, right? I have to know the ground truth. So you have some sort of absolute sensor measurement. Prediction versus correction. So remember this whole thing about tracking and inferences. I make some prediction, I take some measurements, I do my correction. The question is, what's that relative trade-off? Remember we talked about this in Kalman filter, which basically came down to what's the relative size of the noise of my measurements versus the noise of my process? Actually, we usually do the other way around. The noise of my process versus the noise of my measurements. And if one is too strong, you'll ignore the data. If the other is too strong, you'll ignore the predictions. So getting those balanced right is just a little bit of magic that you have to do based upon looking at the data. Here's a more interesting, or I should say fundamental one, and it's referred to as data association. Data association basically is, what if we don't know which measurements to associate with which tracks? So up until now, we've pretty much assumed that whatever we've measured is associated with the thing that we're going to, that we want to keep track of. But in reality, there are a couple things that happen. First of all, there can be multiple objects. That's what this cute little airplane thing is supposed to look like. And in fact, radar, which is where the birthplace of multi-hypothesis tracking came from, had this problem, right? I get a whole bunch of pings back. There's a bunch of airplanes. I got to know which pings go with which airplanes in order to track all the different airplanes. Or there can be what's known as clutter. Clutter means there's a lot of stuff in the environment that has nothing to do with me. By the way, the clutter is the basis of camouflage. So when you take a look at this rattlesnake whose contour you can just barely see here, there's all this other stuff that has nothing to do with it being a snake. So it confuses your visual system. Fortunately, when the snake starts to move, if the brush is not moving also, then you can do the association differently. But in general, clutter means that there are a bunch of measurements that are not from the thing I'm really interested in tracking. The problem is referred to as the data association problem. And the trick is to determine which measurements go with which tracks and which measurements should be ignored, which measurements cause you to start a new track. These are all things that you have to do when you do tracking. So there is a simple strategy, and that's what's indicated here. I've got a point, and I've got the state, and now I take some measurements. I might just associate, I don't know, the closest measurement to my prediction. So remember when we were tracking the contours for the condensation, Izard and Blake algorithm, right? They took the distance to the nearest strong contour, as if they knew somehow that that was the right contour. They just made that assumption. Unfortunately, that doesn't always work. That clutter problem, in fact, one of the points of clutter is for it to confuse something that's trying to do that association. So those of you who watch Tom Clancy movies or read Tom Clancy books like I've done, et cetera, know that submarines will jettison these things that spin around and make noise and bubbles. At least I assume they do. They did in the movies. They did in the book. Now the torpedoes have a data association problem, right? Which thing that's making noise or making a signal should it decide is the real state? Personally, I would think seeing some, many thousand-ton submarine compared to this little thing spinning around wouldn't have been that hard, but obviously the torpedoes aren't that smart. So it doesn't always work in the presence of clutter. There is a more sophisticated approach to doing this, and that is you do what's called multiple hypothesis. So multiple hypothesis says, well, okay, I've seen two things now, and maybe it's one thing, and I should associate the real object with the left measurement, and the right one is clutter. Maybe it's one thing, and I should associate the object with the right-hand one, and the left one is clutter. Or maybe it's two things. That is, a new thing should get created. Well, like I said, there's this whole area called multi-hypothesis tracking where you try to keep track of all these different things. You actually can do this using particles, all right? You can do particle filtering in a not-so-obvious way, right? Each particle is a hypothesis about the current state. So, for example, a particle can say, oh, there are two such objects, and here's where they are. Or a particle could say, there is one such object, and this one is not the right one, etc. So you can do that using particle filtering. And in fact, I one time told Michael Izard, I said, we were meeting, I said, for a lot of situations, I found that particle filtering was just a convenient way of doing multi-hypothesis tracking. And he said, absolutely. So Michael, if you're out there, I remember that conversation. I think he's on the West Coast having a great time, so good for him. The last issue is what's called drift, okay? Drift is the error that happens, that accumulates over time, that basically what happens is you've got this dynamic model that's making a prediction, and you've got its sensor observation model, et cetera, and you're really caught with two choices, okay? And both of the choices are lousy. Choice one is I stick to my target model, right? I really believe the model. And I never change it, like its appearance or its color distribution. The problem with that is what happens if the object is changing? All of a sudden, it goes in the trees, shadows, things look a little different, and I didn't update my model. So almost every tracker does some form of model update. The problem with that is when you do model update, you run into a situation like this. Okay, so this was actually taken from the Tracking People paper, although they were explaining how not to do tracking. So they've got this little box that's stuck on the middle of the ice skater, and each time they're updating something about the description, and eventually the box slides down, and what's not shown here is it might get stuck on the background markings in the rink. And so what's happened is you keep changing, and all of a sudden, more of the target model came from the rink than came from the skater. So as the skater leaves, the model stays right there. And this is the problem with adaptive tracking. And so all real tracking, in order to fight drift, always has this balance between how quickly or how much do I change my model versus how much do I keep what I had from before. And you might ask, well, how come I didn't see any of this in all that Bayesian stuff that you did? The reason is I gave you this sensor model, P of z given x, and I really didn't tell you how it behaves generically, or I should say all the time. In fact, all we did was we generically gave the algorithm. P of z given x might be how well do I match the pixels. Well, but if the pixels are changing, I have to change my sensor model. So that's the place in the algorithm where that notion of how well do I hold on to my old model versus change it, that's the place where it stays. So that concludes this lesson. It concludes the lesson on tracking. It concludes what seems like months of recording about tracking. Somehow this ended up being a lot, but it's really a cool part of computer vision. You have probabilistic state, you have the notion of measurements, and the idea of combining those to come up with what's really going on in the world, which at its heart is what computer vision is all about. Also, for many of you, even if you don't end up doing computer vision, this idea of maintaining a consistent interpretation over time as something changes becomes important. Whether you're tracking the state of traffic flow over a bridge, whatever it is, this idea of maintaining interesting interpretation over time. So some of the principles we learned here from computer vision can be applied to those more generic situations. Anyway, that's it for tracking. Onward and upward, pretty soon we'll start talking about recognition and lots of other cool stuff. See you later.
Thank you.